next week we have a break or
no, next week,
next,
next Saturday, Hiran will
be taking,
do the next one, and then the following Wednesday I will take the session. There are 2 more sessions before the New Year break.
Actually, our committee members also, they are having some questions. They have practiced some. So I told them to send those questions.
To our email,
Yeah.
ssc.general, right?
Yeah. Only thing, as I told you previously, also everyone is now comparing the BS and this one, but I don't think it is a good thing, because if we compare, there definitely there are some some gray areas.
Yes, but the workshop is transition to EUROCODES. So we are assuming that people have some experience with BS. But there are people who are directly starting with the EUROCODES, then they don't have to worry about comparison. This is just to, basically it is to tell people that we are doing roughly the same things as we did in the BS, but with some slight changes.
And share is the most, I think, in the case.
Yeah, that is where the most changes are involved. Perhaps we can start admitting them. Is Kapila there? I don't know who is logged in as SSESL.
Kapila? Good morning, Kapila. මේ හොස් කරනවා නේද? කවුද වෙනගෙන තින්නේ? හරියට දැන් අපි ඇඩ්මිට් කරමුනේ 825 participants. Okay. Good morning, Dr. Nihal Somaratna, Executive Committee, and ladies and gentlemen. This actually we have come to the fourth session of the design course on design of reinforced concrete structures to EUROCODE. So today's session is on design of slabs. So we have already successfully completed session of 3 sessions and moving on to the session 4. So today the resource person for the day is Dr. Nihal Somaratna. Actually, I don't think he needs any introduction to the audience, but as a formality, let me formally introduce him for this audience. But before introducing that, actually, he is the main, I would say, consultant for this design course, and he has did the design of this. Course content has been designed by him mainly, and he has done a lot to this. When we start this design course in year 2022, actually he has done a great job, and he has coordinated from that point onwards. He has coordinated on behalf of the Society of Structural Engineers. He has coordinated among all the resource persons, and so this entire effort actually on behalf of the Society of Structural Engineers, I must thank him for this great work done. In addition to the all resource persons. So actually last year he could not do, he did only one lecture, but so we missed one lecture in this course from him. So this time I think you will be able to get the full benefit of this course from him. So actually I was reminded by him to make a short when introducing his profile. When introducing him to this audience. So I have tried my best to put it very short. So Nihal Somaratna was graduated from the University of Peradeniya with a BSc Engineering in Civil Engineering in 1978. He earned Master's in Science and PhD from University of Illinois at Chicago, USA. After working as a senior structural analyst in auto industry in Detroit, Michigan, USA for several years, he returned to Sri Lanka and joined the staff of the Department of Civil Engineering of the University of Peradeniya in 1991 as a senior lecturer. He served as the head of the department during 2005 to 2008. From 2014, he has been working as a senior lecturer in the Department of Civil Engineering of Sri Lanka Institute of Information Technology, SLIT. He was the head of this department also during 2015 to 2020. Dr. Somaratna served as the chairman of the Board of National Engineering Research and Development Center in 2001 to 2002. In 2004, he was a Fulbright Senior Research Scholar in the Department of Aerospace Engineering in University of Michigan. So with that introduction, now I would cordially invite Dr. Nihal Somaratna to take over to deliver his presentation. Over to you, Dr. Somaratna.
Okay, thank you. Thank you very much, Saranka, for your very kind introduction. Can you hear me?
Yeah.
Okay. I must say that it was a flattering introduction. I can't take the full credit for organizing this workshop, even though I would like to do so. That would not be true. This is a team effort by all the resource persons. Normally, when you have several academics together, it becomes very difficult to come to a consensus because everyone has his or her own opinion. But this a team of resource persons. It was a pleasure working with them. They all were very cooperative and very flexible, and we had no difficulty in planning the workshop or conducting it. I think it is because all of us realize the importance of this type of workshop. That is a very serious requirement at this time in our profession in Sri Lanka. So let me start my presentation here by sharing my screen with you. By the way, if any of you has any questions to raise even during this presentation, please feel free to do so. You can raise your hand and then we will let you speak, or you can send a chat message. From time to time, I will check the chat messages. Let me start my sharing the screen. All right, I assume you can see my screen. Can someone please tell me whether my screen is visible to you? I think everyone has been muted or something. You can send a chat message at least if you can see my screen, please.
Yeah, we can see your screen.
Okay, all right. Thank you very much. So this is the session 4. As Sarangika reminded us, we have conducted sessions 1 to 3 so far. And in those sessions, this is what we did. In session 1, which was conducted by Dr. Premini Hettiarachchi, we discussed the general ideas behind the EUROCODES. Because one of the important features of EUROCODES is that it tries to unite all different structural design aspects, like whether it is steel or concrete or timber or aluminum. They want to show that there is a certain amount of common information for all these. And these were covered in session 1, which dealt with the design philosophies, the loads that should be used, and the values of various factors and so on. They are common to all the materials, regardless of whatever material you are going to use for your design. Then in session 2, which was conducted by Professor Priyan Dias, we looked at how to handle texture in reinforced concrete elements. Even though it was taking beams as the example, basically it was dealing with the phenomenon of flexure. Whenever we apply loads on any structural member, it is possible that it will be subjected to bending moments, and that is a flexure. How do we handle that? How do we provide reinforcement to cover that? Then in session 3, which was conducted by Dr. Hiran Yapa, we looked in a similar way at how we can handle the phenomenon of shear stresses developing in our structures. Once again, beams and at some points slabs were used as illustrations. But this also was about this particular phenomenon, shear stresses developing in our structural members. So after this first 3 sessions, I think we are in a position to handle most types of structural members that will be subjected to flexure or shear. The philosophy of the EUROCODES is to say that it doesn't matter what the actual member is, whether it is a beam or whether it is a slab or whether it is a column. The important thing is to recognize that when they are subjected to external loads in their cross sections, they will develop flexure and shear and sometimes axial forces also. So if you look at what we are going to do in the current session, we say it is about design of slabs. If you look at slabs and if you apply loads on slabs, bending moments and shear forces will develop in cross sections of the slab. And sometimes there can be some torsion also, that also will give rise to shear stresses. So we are now equipped to handle this. We know how to handle friction. We know how to handle shear stresses and so on. Therefore, in this session, what we are going to do is we will see how we can apply the ideas that we discussed in the previous sessions into this particular type of member, that is slabs. So in that respect, I think we should find it a little easy to talk about design of beams, because the previous sessions we covered the basic ideas required for design of such members. So the main issue that we need to look at here is this. Normally, we have to first analyze our structure to find the internal forces, moments, etc., that will develop in cross sections. After we find those, we can design the reinforcement in those sections using what we have already discussed. Therefore, today we will try to look at the general guidelines given in the EUROCODE for analysis, that is in addition to design, which we have already discussed. Therefore, I think today's discussion will be more about analysis of slabs to find the internal forces rather than how to design the sections which we have already discussed. So let us go forward from here. Now, in my opinion, one of the main objectives of our workshop is to not to tell you how to do designs, but we want to show you how you can yourself find the necessary information to do your designs. Because otherwise, every time something changes, you have to again find how to do it. It cannot be done all the time using other resource persons. We need you to develop your abilities to go through this code and figure out for yourself what needs to be done. This is the process that we are going through now. There are 2 categories of people. One, the more senior or experienced people, they may already be quite familiar with the use of the previous British standard. And they are the people who are transitioning from British standards to EUROCODES. Then there might be another group of people who have a few years design experience, but who have started designs using EUROCODES. Because I remember at Peradeniya, we started teaching designs using EUROCODES around maybe 2010. So people who have gone through the course after that have started their design careers with EUROCODES, and there's nothing to transition. They are familiar with the EUROCODES. So for that group of people, this workshop will be a kind of refresher course and a unified presentation lasting several sessions to tell you how you can handle EUROCODES in our designs. Now, in the United Kingdom, Britain, where we have been following mostly our designs had been done according to the British standards earlier. In the UK also, they went through the same procedure, because around 2005 to 2010, they also had to adopt the EUROCODES. So during that time, they had this transition, and there were many publications that tried to help people during this transition. So I am just citing two such publications. The first one is this Manual for the Design of Concrete Structures to EUROCODE 2 by I. Structi, that is the Institution of Structural Engineers, UK. That is a very nice small manual that guides us through how to do various designs of different members according to the guidelines given by the EUROCODES. So I strongly recommend that you try to get yourself a copy. I think if you search the internet, you would be able to find that. The second reference is the Designer's Guide to EN 92-1-1 and EN 92-1-2. By the way, we are only considering EN 1992-1-1, which deals with the design of reinforced concrete buildings. The authors are Narayanan and BB. Both of these people have had long periods of experience dealing with the development of these codes, both the previous British standards and the EUROCODES. So they are very knowledgeable, and this designer's guide gives a fair amount of details about the development and the reasoning behind the EUROCODES. So that is also a very useful reference. Then there are several good textbooks. I'm just citing two, not to say that they are the best, but they are reasonably good. The first one is Reinforced Concrete Design to EUROCODE 2 by Mosley, Bungie, and Halsey. Mosley and Bungie started this textbook a long time ago. They first wrote it for BS codes, and then late editions, I think the 7th edition, deals with EUROCODE. So that is also a very good textbook that explains most of these things in very simple terms. Then I am also suggesting that this second textbook, Design of Structural Elements by Chanakya Arya, is a useful reference, but it is not something as detailed as the previous one by Mosley, Bungie, and Halsey, or the previous one by Narayanan and BB. The book by Chanakya Arya gives you some simple guidance to do designs according to EUROCODES in the case of simple elements. It also discusses in parallel how to do the similar designs using the previous British codes. If you are transitioning from the British standards to the EUROCODES, that might be useful for you. But for people who have started on the EUROCODES without any experience with BS, you don't have to worry about this transitioning part. You can simply look at the guidance for design using EUROCODES. I think it will be very good if you can get some of these, at least some of these references, so that you will be able to get more information. In this workshop, we can provide you only some basic information and guidance about EUROCODE 2. Now, I was present in the previous sessions, and I also noted the various discussions, the questions that were raised, and so on. So I feel that I should make a few comments before we start talking about SLAB, that I need to make a few comments about general comments about the EUROCODES. In Sri Lanka, when we are trying to do designs, there are 3 different groups of codes that are relevant to our discussion. The first set of codes is the original European standard, the EN codes, what we call EUROCODES. Okay, there is a set of codes published by the European Committee for Standardization, which is abbreviated to CEN. It is from different languages. The European Union, these codes use 3 languages as their main language: English, French, and German. So some of these things are coming from French or German versions, these abbreviations. So that is the source of all our codes. The EUROCODES are coming from this particular organization. But to have some legal status, these codes have to be adopted by different countries. It is only after each country adopts the EUROCODE that it becomes accepted standard in that particular country. So Sri Lanka has done that to some extent, at least. So Sri Lankan Standards Institute, SLSI, has adopted these EUROCODES, and they have been published as SLS-EN standards. So that is another group. And you know the concept of a national annex. When you try to develop a code that can be applied to many different countries, which might have very different local conditions, it is almost impossible to come up with a single document. So what the people who drafted the EUROCODES did was, they said, okay, the main basic principles are given in the main code, but each country has the freedom to change some of the parameters and values given in the code to suit their local conditions. And these changes are shown in what is called the local annex, the national annex. So when Sri Lanka adopted the EN standards, it also published relevant national annexes. And then the third group is the EN standards as adopted by the British standards. So they have the prefix BSEN, then a number. So they form the third group that we might be dealing. So these are the 3 groups. And sometimes this can cause a little bit of confusion as to, okay, which of these groups should we use? In that respect, please note that guidance in the national annex for the same EN code can be different from one country to another. That is the national annex. But the main code is identical. It does not change. That is one thing. The second thing that we have to be aware of is that these standards are not static. They are not fixed. They keep changing. They are living documents. So from time to time, they undergo some changes. Therefore, when we refer to a particular standard, it is important to say the year of publication so that we know exactly which version of the document that we are talking about. I'm sure you know these things. Forgive me if I'm telling you things you already know, but I just want to make sure that we all understand these things clearly. These are the 10 EUROCODES that form the group of EUROCODES. And the first two are the ones that deal with the basic general idea that we refer to them as the material independent topics. And this was covered in session 1. And then we come to EUROCODE 2, design of concrete structures. That is the subject matter of the subsequent sessions, session 3 to 8. Now, if you look at any country's adoption of an EUROCODE, this is what you will find. The yellow pages here is the EUROCODE published by the CEN, the European Standards Committee. And then when a country adopts it, they can have these yellow pages also. In the front, you can have a national title page and a national forward. Then the actual original EUROCODE as published by CEN. And then at the end, you have the national annex. For a particular country, the particular EUROCODE, for example, BSEN 1992-1-1 will mean this entire collection, including the national annex. Similarly, when we have the SLS-EN 1992-1-1, for example, if you refer to that, it means the EUROCODE plus the national annex. The EN code, that is this yellow part, is the same for all countries, but the national annex can be different. So when the British standards adopted the EUROCODES, they became their main codes. From 2010, the other codes, previous codes, were withdrawn. Withdrawn doesn't mean that they are not good. Withdrawn simply means that they will not be updated anymore because the EUROCODES are there. The EUROCODES will be updated from time to time. Sri Lanka standards adopted, and they are referred to as SLS-EN, then the number. And SLSI has published the relevant national annexes also. So when we refer to SLS-EN 1992-1-1, it means the EUROCODE plus the national annex. So just to give you an example, this is the front page of the SLS-EN 1992-1-1. Then there is a colon and the year of publication is given here. So this SLS-EN 1992-1-1 was published in 2012. But at the bottom it says this Sri Lanka standard is the identical implementation of EN 1992-1-1 :2004. So what we have adopted and published in 2012 is the 2004 version of EN 1992-1-1. Okay, so there has been a gap of several years. But in the meantime, this code also changes. So, for example, they published EN 1992-1-1 of 2004, that is the original publication, plus A1. Here, what they did was they added certain additional changes and additional information to what was published in 2004. There are several terms that they use here. Corrigendum is correction of errors. Addendum means include additional material. Amendment means modify the contents. So this one, they say, incorporating corrigenda of January 2008 and November 2010. So that is now slightly different from the original version. And then the British standards immediately adopted that. This was the CEN published this in 2014. The British standards also published, accepted, adopted that and published it in 2014. This is that title, BSEN 1992-1-1, colon 2004 plus A1, that is this part. Again, colon 2014, saying that this British standard was published in 2014. Now, Sri Lankan standards still has not adopted this part. So Sri Lankan standards is still going with a previous version. Okay, so this is the British standard adoption. It gives that title here. And then it also notes what are the changes that were included. Now, when it comes to the local annex, Sri Lanka National Annex to Eurocode 2 is published, and that was published in 2013. But it is to be used in conjunction with SLS EN 1992-1-1 of 2012. So that goes together. Now, let us consider this. A contract for a building in Sri Lanka says, reinforced concrete designs shall be carried out according to relevant Eurocodes. Now, if you are the designer who is going to do this design, what is the code that you will use? We have several options. We can use EN 1992-1-1 plus A1 published in 2014. That is the original Eurocode. Or we can use the adoption of SLS EN 1992-1-1 in 2012, or we can, if you are used to going to the British standards, you can go to this. So which one would you use? Can you use chat box to tell me what you will be using, A or B or C? Any suggestions? Okay, I see someone has raised a hand. Can the host unmute that participant?
So the chat box is disabled, sir. That's why I raised it. Hello, sir. Can you hear me?
Yes, yes.
So the chat box is disabled. We can't do any chat messages. That's why I raised that.
Oh, I'm very sorry about that. Can the host allow participants to write in the chat box?
Answer would be B, sir.
Okay, right. The host, please make a note and allow participants to write in the chat box. So the answer is B. That is, we should use the SLS in 1992-1-1 published by the Sri Lanka Standards Institute. Yes, that is a reasonable approach to take. But see, this statement says reinforced concrete design shall be carried out according to relevant EUROCODES. So I hope you can see that this can lead to some confusion. Someone can say that relevant EUROCODES means this A. So the question is, should we be using A or B? I think the answer given is more reasonable, that we should use B. Why? Because if you use A, the EUROCODE, it does not have a national annex. So we will be compelled to use the recommended values in the EUROCODE, which most probably are what is suitable for European conditions, even the recommended values. Therefore, it would be better for us to use some code where the Sri Lankan national annex is available. That is this answer B. But the downside is that this is not based on the most recent version of the relevant EUROCODE. So there is a little give and take here. But I think you are right. If we were to do this, we should use the most recent version of the adoption of the EUROCODES by the Sri Lankan standards with the relevant national annex, because this national annex is very important. For example, in the last session, Dr. Hiranyappa showed you how our national annex has changed some entries in the main code about the shear stress in high strength concrete. For example, our Sri Lankan national annex has given some different guidance. So we should be aware of those and use the proper code. And the other thing is, I am not a lawyer, so I can't say exactly what is legal, but these are things that have come up in discussions with knowledgeable people, design engineers, and so on. If you are going to, it is a good idea to, if it is a big project, it is a good idea to specify exactly what code should be used for the design. But something like this is not very specific. Reinforced concrete design shall be carried out according to relevant EUROCODES is not very specific. So it would be better to specify the particular codes that you want to be used, so that any disputes in the future can be avoided. So please keep that in mind. Now, this is just for sake of completion. You know these things. The similarities between the EUROCODES and the previous British codes is that they both use the limit state philosophy. They both use the method of partial factors. So the philosophy and the procedures are the same. Similar modeling of behavior materials, concrete and steel also basically model similarly. Similar methods of structural analysis. So those are good features, because what this means is what we have done in using the previous British standards can be used here also. But there are some small differences between EUROCODES and previous British codes also. These are the differences. They are mainly difference in style. Style of presentation is a bit different. In the previous BS codes, they gave one chapter for each type of element. There was one chapter on design of beams. There was one chapter on design of slabs, and one chapter on design of columns, and so on. Okay, so it is arranged on the basis of element types. But the EUROCODE doesn't do that. It says it doesn't matter what the member is, whether it is a beam or a slab or a column. What happens is the the phenomenon that will arise from the loads, whether it is flexure or whether it is shear or whether it is axial forces. The EUROCODES say that is all you have to worry about. Whatever the member is, you worry about the particular type of action effect. They call it action effect, and then deal with it. Another difference is guidelines on application of design procedures in EUROCODES is less detailed than in the previous British codes, especially about analysis procedures. The EUROCODE is allowing the designer more flexibility, saying these are the basic ideas, then you can decide how you want to do the analysis. Whereas the British standards, earlier ones, used to be more specific. They said use this method, and this method for the analysis. Other differences you already know. The EUROCODES are always dealing with compressive strength in concrete, FCK. Then something that can cause confusion is use of comma as the decimal point. We have to be careful. Then terminology also is slightly different. Actions, verification, execution, etc. You have seen this earlier. Actions, generally we used to call them loads. Verification means checking. Execution is the construction, and so on. And the EUROCODE uses symbols and expressions a lot. So we need to get used to interpreting the symbols and interpreting the expressions. Now, as an example, this is BS 8110-1, the old British BS standard. It says design and detailing reinforced concrete. And then under that, there are different sections: beams, solid slabs, rib slab, flat slabs, columns, walls, staircases. So it goes with the member type. And then the same thing is done for pre-stressed concrete separately. But the EUROCODE says all these things are the same. So in the EUROCODE, it says here, ultimate limit state, bending with or without axial force, shear, torsion, punching. These are the effects of the loading regardless of the member type. So EUROCODE has been organized based on these things. So sometimes we might feel that it is a little bit cumbersome, because if you want to design, for example, beam, you had to consider bending, then you had to jump to this section about shear, and then you had to go into this section about torsion, and sometimes you had to go into this section about punching, and so on. So they are not collected together in one place, but it has its advantages and disadvantages. If you look at the EN 1992-1-1, there are different subparts. Part 1-1, general rules and rules for buildings. That is what we are dealing with. And in that part, there are sections. See, the sections are general basis of design material, durability, structural analysis, ultimate limit states, and serviceability limit states. And then detailing. Under the ultimate limit states, as I showed earlier, they deal with the phenomenon: flexure, shear, torsion, etc. There is a certain logic to this presentation also, but it is slightly different from what we are used to from the British standards. So we had to get used to this way of doing things. So we come to the main topic. We have already handled the first 3 sessions. In this current session, we need to look at how to design slabs. And mainly it is dealing with how to analyze slabs to find the bending moments and shear forces that will develop in cross sections of the slabs. You will be happy to see this slide, I hope. the design of slabs is less complicated than design of beams. Normally, we would have thought the other way. But why is it less complicated? This is nothing to do with EUROCODES. This is, in general, slabs are less complicated because the width of the slab is already known. When you start the design, you know the dimensions of the slab, so the width is known. And very often what we do is we take a representative unit width of the slab and do the analysis. So the width is known, or we can limit it to 1 meter or 1 unit. Now, in most cases dealing with slabs, where the thickness is somewhat small, say 200 millimeters or less, most of the time, singly reinforced sections are sufficient. So we don't need to use compression reinforcement for dealing with flexion. And in most cases, shear reinforcement is not required. That is the strength, the shear strength of the concrete alone without any shear reinforcement is sufficient to resist the shear forces developing in slabs. So you can see this is less complicated than a beam. Now, under slabs, we will be trying to look at these different things. Now, if you say slabs, there can be solid slabs, there can be rib slabs and precast slabs, and then waffle slabs and various other things. But today's presentation, with our limited time resources, we will try to look at solid slabs only. And when it comes to solid slabs, we will look at solid slabs on linear supports. What we mean by linear supports is a straight support. There can be walls or beams, so they are supported, solid slabs supported by beams or walls. And they also will be subdivided into one-way spanning and two-way spanning slabs. Then another type of solid slab is the solid slabs which are supported only on columns. They are flat slabs. So we will try to look at these different categories. There is a message on the slab. When we design a cover slab, width is less than 1 meter, should we consider 1 meter or actual width of cover slab? Okay, so I hope you understand the question. Sometimes we can have a slab whose width is less than 1 meter. So in our analysis, should we use 1 meter as the representative width or the actual width of the slab? The answer is you can do it both ways. But you have to be careful. You have to think carefully about the method that you use. What I would do if I were to do the design is take a representative strip of 1 meter width and then calculate, say, the bending moments, shear forces, and so on. That is per 1 meter. And then to design the reinforcement also, you can design the reinforcement saying over a 1 meter width, you need to provide 5 10 millimeter bars, for example. And now you say the actual slab width is, say, 0.8 meters. Therefore, you multiply your bending moments and shear forces by 8 to see what are the actual bending moments and shear forces on your slab. And then the reinforcement also, if you are thinking about the area of reinforcement, if you have already calculated the area of reinforcement per unit width, then you will have to multiply that by the width, actual width, which is 0.8 in this case, as an example, so that the area of reinforcement required will be less. And then you can provide the necessary reinforcement. On the other hand, you can start from the very beginning saying that the width of the strip is the width of the slab. That is fine. But then when you are calculating, when you are estimating the bending moments and shear forces, you have to be careful. You have to remember that the width of the strip that you are considering is not 1 meter, but it is the actual width, which is 0.8 meters. When we come to estimating the bending moments and shear forces, I will point this out. Okay, that is a very good question, because it brings out this particular aspect that we have to be very careful when we deal with this. Right, in all these different cases, the steps that we had to follow are basically the same. We had to determine the loads, and then we had to do the initial sizing. Now, when it comes to a slab, you already know the floor plan, the locations of the columns, and if there are beams, you know all that. Therefore, by the time you come to this stage, you already know the dimensions of your slab. Okay, so initial sizing simply means deciding on a reasonable thickness for the slab. Once you do that, find the loads and come up with a reasonable thickness for the slab, then we can go and analyze for bending moments and shear forces in critical sections, important sections where we have the maximum effects. And once you find them, you design the sections according to what we have discussed in sessions 2 and 3, flexure and shear. And then we should be concerned about the deflection also. So we do a deflection check. And if everything is okay, then you can decide on how to detail the reinforcement in your slab. These are the basic steps that we need to follow. And the EUROCODE gives guidance on each of these sections, but the extent of details is, it varies from section to section, from topic to topic. The main thing is that the EUROCODES allows the designer some freedom to decide how he or she wants to do the design. But in order to get the benefits of that freedom, we need to understand clearly the procedures that we are using. We should not just use things blindly, because we might end up making mistakes. So we need to understand the basic ideas behind our analysis methods and design methods and so on. And that is the objective of this workshop. Now, when it comes to guidelines in EUROCODE 2 on analysis of structures, there is good news and bad news. So let me tell you the bad news first. The bad news, I have extracted a statement from the book by Narayanan and Beebe, where they say this: EN 1992-1-1 provides limited guidance on analysis. Basically saying not very detailed. Elastic analysis remains the most popular method for frame. Now, elastic analysis means the type of analysis that we are used to doing, right? As undergraduates, we learned how to do structural analysis, how to analyze beams, how to analyze frames, how to analyze columns, and so on. They were basically elastic analysis based on linear elastic method. So that is the elastic analysis method that they are referring to. There are different methods that we can use to do that analysis. We can use, for example, moment distribution. We can use slope deflection. And I think we should add one more thing here. Now that has become, I think, the most widely used method, that is computer-based techniques, numerical methods. mainly finite element programs, can be used to analyze beams, frames, everything very, very easily and quickly. But you need to know how to model your structure and feed that information to your computer programs. After that, the analysis is done. So these methods, which we refer to as classical methods of analysis, moment distribution, slope deflection, etc., are very good. We can use them for simple problems, but if we have more complicated problem, and if we want to analyze the entire complicated structure together, then we will have to use finite element methods, which are basically finite element programs, which are now available very, very widely. I think almost all design officers will be using that. So that is the bad news. The EUROCODE gives only limited guidelines on analysis, but there is good news also. This is the good news. The good news is that general guidance in the EUROCODE 2 regarding analysis is similar to what has been used in previous BS codes. So they are basically doing the same thing. Therefore, most of the design aids related to analysis available in previous BS codes, for example, BS 8110, it gives various tables and graphs and so on to help us do the analysis. It summarizes the results of analysis so that we do not have to repeat those analyses. They have done it for us. We can use that. Because the EC2 also is advocating similar methods, we can still use what was available in the BS 8110, for example. They can be used with the EC2 also. So that is the good news. We can still use those design aids. We will see how we can do that. Now, guidance in Narayan and BB's book, The Designer's Guide, says when we analyze for forces, moments in members in braced structural frames. Now, you understand what is braced structural frames. That is when you have a large structure. There are two types of loads that they have to carry. One, vertical loads due to imposed loads, live loads, dead loads, everything vertical. And then there can be horizontal loads, wind loads, etc. So very often in our structures, we provide specific elements to take care of the horizontal loads, like shear walls, and sometimes some bracing. So if there are specific elements that are used to resist the horizontal forces, then the other elements, the main part of the element, main part of the structure, do not have to carry those lateral forces. They only have to carry vertical forces. That is what is meant by braced structural frames. They are braced against lateral forces, but separately. The main part of the building is only to carry vertical loads. Then you can use what we call sub-frames. Instead of analyzing the entire structure, if you take one frame, one plane of a big building, it might look like this whole thing. But if we are going to use simple analytical methods, it is going to be a nightmare if we try to analyze some big frame like this. So the guidance in our codes has been, you can consider parts of the structure separately and analyze them. For example, you can consider one beam like this. You just cut the beam and the top and the bottom columns and separate it and make certain assumptions about the column stiffness, etc. You can analyze that. If even that is too complicated, you can consider one span at a time, like considering These are general guidelines that you are all familiar with, I think. We can use them to simplify our analysis of these different elements. And this subframe analysis was quite useful in the past. Even now, if we are just going to look at a particular member in a large frame, they can be still used. But now, more and more numerical methods, finite element methods are taking over this part. Now, one of the simplifying subframes that is recommended in analysis, if you have a beam like this beam, one way to analyze that is to forget the columns and just say the columns are like simple supports. So they only provide reactions, they don't resist rotations. So the beam can be thought of something like this. The beam, where the columns are, you just provide simple supports. Or if you are only looking at a particular column, you can go even for something like that. So these were the guidelines that were used earlier, and that is explained in the book, the textbook by Narayan and Bibi, and you are quite familiar with this. Now, when it comes to the analysis of slabs, it is to determine bending moments and shear forces. These are the things that we had to do. We had to find the loads on the slab. Then we had to consider what is called pattern loading. We'll come to that. You know that, I think. Then use some method of analysis, and then design aids we can use for that analysis. And after that, we had to do the next part, the design and detailing. So I told you the objective of this workshop is to show you how you can find the necessary information. Therefore, very often in this presentation, I am going to tell you what is given in the code or the manual, but I will indicate the source. For example, now we're talking about idealization of the structure. This is coming from EN 1992-1-1 or 2004. This E refers to the English version because they published this in the 3 languages, English, French, and German. So this is the English version, and these are the guidelines. So the purpose is, I hope you will go to your copy of this EN code and look at these things in more detail. We will not have time to go through all the details, but we will go through the main ideas, and I hope you will go to the necessary documents and get more information. So the idealization of the structural models for oral analysis, they give these guidelines. Structure, the elements are classified by consideration of their nature and function as beams, columns, slabs, etc. Rules are provided for the analysis of the commoner of these elements, more common types. For buildings, following provisions 3 to 7 are applicable. Then 3 to 7 is given here. A beam is a member for which the span is not less than 3 times the overall section depth. Now see, the point is, in these guidelines, they tell you exactly what they mean by each of these terms. Now, this, without any ambiguity, it says what can be considered a beam. A slab is a member for which the minimum panel dimension is not less than 5 times the overall slab thickness. So if your slab thickness is 200 millimeters, 5 times that is 1 meter. So your panel dimension should be more than 1 meter for you to think of that as a slab. Then a slab subjected to dominantly uniformly distributed loads may be considered to be one-way spanning if either it possesses two free parallel edges. If two edges are free, then the loads will be going to the other two edges, so that it will be spanning in one direction. Or it is the central part of a rectangular slab supported on four edges with a ratio of the longer side to the shorter span greater than 2. So that is what we have been using all this time, right? Ly divided by Lx. If it is less than 2, it is two-way spanning. If it is more than 2, it is one-way spanning. But did anyone ask, why did we use this magic number 2? Because this is a gradual change, okay? 2 is an arbitrary limit. Why don't you use 2.5, or why didn't you use 1.8? We have no answer, but in practice, it has been found that it is reasonable to have this boundary at 2. But if someone says, how can you say that? You know where that guidance is given. We can say the Eurocode 2 in 531, paragraph 5, it says that if this ratio is more than 2, it is one-way spanning. It doesn't say what is two-way spanning, but we have to understand if it is less than 2, it is two-way spanning. So these are examples of one-way spanning slabs. If you have a slab here supported by beams or walls like this, then it will be spanning, the loads will be transferred to the walls or the beams by spanning in this direction. And that is the span direction, and it is one way. It does not go the other way because there's no beam or wall to send the loads to. But here, if you have beams or walls all the way around, then the loads can, if you consider this, and loads can go either sideways or you can go to the other side. Then if Ly, that is the larger length of the panel, Ly, is larger than 2 times the short length, then we approximately, most of the load will be going this way. So we can design that as a one-way spanning slab. Now the loads, which are referred to as actions in the Eurocode, you saw this from EN 1991-1-1. They give different categories, category A, B, C, and so on, D, E, F. And the specific use, they say category A is areas for domestic and residential activities, etc. B is office areas, and so on. And here they give examples. So we can decide, when we have to design something, we can decide first what is the category to which the slab belongs, depending on the usage. And then the code gives the different loads. QK is the distributed, uniformly distributed load that you can use, given in kilonewtons per meter squared. So for category A, for example, if it is floors, the value is 1.5 to 2.0. And they give only a range. So as the designer, you can pick 1.5, 2, or anything in between. So that requires a certain amount of consideration on your part, considering the particular building you are dealing with and considering the intended use and so on. You will have to decide this. But if you are unable to come up with any reasonable justification for selecting anything other than this highest value or lowest value, the code says they give some recommendations. Okay, the recommended values are underlined here. You can see the underlined values are the recommended values. If you don't have any other way to decide, you use the recommended values. Then this is another idea that has been used in previous codes also. Reduction of imposed loads based on the loaded area. The idea is that, all right, the values given here is uniformly distributed load over the entire area of the slab. But it is extremely unlikely that if you have a large slab, that everywhere at the same time, this maximum possible loading will be acting. Especially true for large slab. If the slab is small, you can say, well, there is a good chance that the entire slab will be subjected to these loads. Therefore, we have this idea. Based on the loaded area, you can reduce the load somewhat, saying that this load might not be acting over the entire area. This idea in the past was called live load reduction. Please note that this is only for imposed load, not for the dead load. Okay, dead load is there all the time and everywhere it's the same. Imposed loads or live loads, but we used to call them live loads. So this was in the past called live load reduction or LLR. This is what is given. Imposed loads. Now I am showing how we get to this. Okay, this is EN 1991-1-1 2002, section 6, imposed loads on buildings. Then we go to section 6.2.1, floors, beams and roofs, and then the paragraph number 4, it says imposed loads from a single category. Single category means category A, B, C, D, etc. If a particular area, a particular panel of a slab, for example, is subjected to a particular category only, single category may be reduced according to the areas supported by the appropriate member by a reduction factor alpha A according to this clause. So we know where this comes from, and that particular clause is this. A reduction factor alpha A may be applied to the QK values for imposed loads. These are the recommended values of alpha A. 5/7 psi 0 plus A naught over A. But it should be less than or equal to 1. If it is to be a reduction factor, of course, it has to be less than or equal to 1. If it is more than 1, it is going to increase. So reduction factor means it should be less than or equal to 1. But with the restriction for categories C and D, alpha A should be greater than or equal to 0.6. But otherwise, this is for categories A to E. Remember the categories A, B, C, D, like that, E also is there. So for those categories, this is applicable. And this is how you calculate alpha A. But for category C and D, there is a limit on alpha A. Psi naught is the factor according to EN 1991. Psi naught is defined in the code EN 1990. EN 1990. This is an extract from the instructive manual, but it gives the values recommended in the EUROCODE, EN 1990. So you can see for most of these things, it is 0.7. So this psi 0 is going to be 0.7. Therefore, this 5/7 times psi 0, 0.7 will, the whole thing will work out to 0.5. So alpha A is 0.5 plus this much. So if it is to be any use, this A0 over A should be less than 0.5. A0 is the reference area that is given as 10 meters squared. So for A0 over A to be less than 5, the area of your slab should be larger than 2 times A naught. That is 20 meters. So this will be effective only if A is larger than 20 meters square. If that is the case, then you can use this to reduce the value of QK for your slab. So I have a small question here. What we are going to do is we will take a little break now, and we'll take a 10-minute break. The time now is 9:45. So we will come back at 9:55. But during the break, if you can take a look at this particular case, when we come back, you can tell me what you think is the load that we should use for this particular situation. To decide on that, you will need to look at the loads given in this table. Assume that we are talking about flows and the ideas given in this imposed load reduction, and then we should be able to come up with an idea here. So we will take a break here, and we will come back in 10 minutes.
Sir. Hello, sir.
All right. Let us get back to our little question here. I have some responses in the chat box. C or D, 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 D. So those are the responses I have received. They are all correct in the sense they all can be justified. They all are justifiable values. Actually, if you think about it, all these 4 values can be justified for this particular application. Okay, so this is the way I would look at it. Now this says this is for residential purposes, load category A. I have specified that, and it's a floor slab. So first thing is to find what is the basic load recommended for that category A floors. The value of QK is 1.5 to 2. Therefore, as the designer, you can pick 1.5 or 1.6 or 1.8 or 2. But then, how can we decide whether it should be 1.5 or at the other extreme 2? If we have a good idea about the intended use of this particular structure, then you might be able to pick some value between these 2 extremes. For example, if you say look at A, category A, examples are rooms in residential buildings and houses, bedrooms and wards in hospitals, bedrooms in hotels and hostels, kitchens and toilets, etc. So without knowing exactly what the intended purpose is, I would be a little hesitant to go to the lowest end of the range, that is 1.5. But if I know that it is basically going to be housing units or something, then I think 1.5 would be okay, because in house you are not going to have very heavy loads distributed over the entire area. But if it is something else, say wards in hospitals, especially in our hospitals, we might have more crowded situations and so on. Therefore, if you are not very sure about the particular intended use, it might be better to go towards the higher end of the range. And in fact, the recommended value they are giving is 2. The underline is 2. So we can say 2 is a reasonable value. But even if you pick 1.5, provided you can justify it, that is okay. Therefore, 1.5 kilopascals and 2 kilopascals are okay. But we note that this panel is 5 meters by 6 meters, so the area is 30 meters squared. We immediately remember, okay, now this is more than 20 meters squared, so that we can use live load reduction. So here, we calculate alpha A. Size 0 is 0.7 for domestic residential areas, 0.7. So 5 over 7 into 0.7 will be 0.5. A naught is 10. A is 30. So that is 10 over 30. So the answer will be 0.83. So that is alpha A, and we can multiply the loads by that value. That is saying that in this large area, we can't expect the whole area to be loaded with the maximum load at the same time. So if you multiply 1.5 by that value, you get approximately 1.25. You multiply 2 by that value, you get 1.67. Therefore, you see, all these can be justified, but if I were doing this, most probably I would try to pick D because I don't know what the intended use is. So I will go to the highest value, and that is the recommended value 2, and then use the live load reduction alpha to make it 1.67. But you see that you can use anything from 1.6, 1.25 to 2. So as a designer, you have a fairly important responsibility to decide what is the value that you should use. If you use a smaller value, you have advantages. The member sizes will be small and the cost of the building will be smaller. But smaller values might mean higher risk. So can you justify that? If on the other hand, if you use the higher end 2 as the value of Q, then you are playing fairly safe and you can use the reduction to get 1.67, something like that. Okay, so please understand that as a designer, you have some important role to play in this decision. Then we come to section 5 of the EC2 1992-1-1. This is about structural analysis, and then they give various details. And then load cases and combinations. These are the 2 load cases and combinations that they have recommended. Okay, where a simplification in the number of load arrangements for use in a country is required, reference is made to its national annex. The following simplified load arrangements are recommended for buildings. So these 2 are recommended by the EUROCODE. Alternate spans carrying the design variable and permanent load, gamma Q capital QK plus gamma G capital GK plus PM. Don't worry about this PM, that is coming from pre-stressed forces. We don't have that. So it is gamma Q times QK plus gamma G times GK. That is alternate spans. The other spans carrying only gamma G times GK. So this is simply saying alternate spans to be loaded with the permanent loads or the dead loads plus imposed loads, and the other spans to be loaded only with the dead load. But please note that the same value of gamma G should be used in both cases. That is the partial factor, 1.35 for permanent action should be used in both cases. In the past, they allowed use of a lower value for the spans where you want low loads, but now the thinking is what we say, it is loads coming from a single source. The single source is the debit of the slab. So you can't say in different panels the slab thickness is going to be different and so on. Therefore, you have to use the same partial factor in both cases. Then the second way to arrange is any 2 adjacent spans carrying the design variable and permanent loads, all other spans carrying only the design permanent loads. So those are the 2 arrangements they have recommended. But please remember that in our national annex, SLSEN 1992-2012, I'm sorry, this is, I'm giving you the particular section that says all permanent actions from one source, such as self-weight, should be multiplied by the same partial safety factor. That is for your information where it is specified. In this clause also the same point is given. But please note that when it comes to Sri Lanka decision in the national annex, they give a third option. The first options are what is given in the EUROCODE. The third option is here for slabs. Use the all spans loaded arrangement described in B1. All spans carrying the design variable and permanent loads. If these conditions are satisfied. 1, in a one-way spanning slab, the area of each bay exceeds 30 meters squared. 2, the ratio of the variable load QK to the permanent load GK does not exceed 1.25, and 3, the variable load QK does not exceed 5 kilonewtons per meter squared. If all these 3 are satisfied, you can use this option. There is some further description. When analysis is carried out using the load arrangement described in D1, that is the same case, the resulting support moments, except those at the supports of cantilevers, should be reduced by 20%. So the support moment should be reduced by 20% with a consequential increase in the span moments. Now, this is normally the easiest thing to do. If you have a slab and you want to analyze it, the easiest thing is to load the entire slab with this recommended load and then solve it. And then if you want to, you can reduce the support moments by up to 20%. This is because you can use finite element packages to do this analysis, even if you have a large flow slab. It doesn't matter, even if you want to model the entire building, it is not going to be difficult, so that you can do this easily nowadays. Okay. Now, for the meaning of bay and panel, this is a diagram given in the old previous BS 8110. Panel is this part, bounded by 4 adjacent columns. Bay is the entire area bounded by 2 boundaries across the entire width of the slab. Okay, so this is a bay, this is a panel, just for your information, in case you wonder what it is. Then in this section 5 again, general requirements, they say common idealizations of the behavior used for analysis are linear elastic behavior. Now, as I told you earlier, this linear elastic behavior is what we have used in our structural analysis all the time, is linear elastic behavior. Then there is the second one that says linear elastic behavior with limited redistribution. These 2 are the ones that we use for slabs mostly. The other 2, plastic behavior, including strut and tie models, nonlinear behavior, we normally don't go to that extent in our design of slabs. So we will only look at these first 2, linear elastic behavior and linear elastic behavior with limited redistribution. Once again, please note that now you know the source of all this, okay? From EN 1992-1-1, these are the sections. So linear elastic analysis, they describe linear analysis of elements based on the theory of elasticity, may be used for both the serviceability and ultimate limit states. For the determination of the action effects means bending moments and shear forces, etc., you can assume uncracked cross sections. So even if you have beams or slabs, you know, with reinforced concrete, you might have cracked sections, but they say don't worry about that. You can do the analysis based on uncracked cross sections, linear stress-strain relationships, and mean value of the modulus of elasticity. Now, if you go and look at the table given in the EC2 to give the different properties of concrete, they give 2 values for modulus of elasticity. One is the mean value, the other one is the characteristic value with 5% limit. So what this guideline says is use the mean value of the elasticity. Then about linear elastic analysis with limited redistribution, the important part is this redistribution. Linear analysis with limited redistribution may be applied to the analysis of structural members for the verification of ULA, that is checking ultimate limit state only. Whereas linear elastic analysis, they said, can be used for both serviceability and ultimate limit states. But at the design stage, we will be worried about the ultimate limit states, so we can use redistribution also. The moments at ultimate limit state calculated using a linear elastic analysis, that is doing linear elastic analysis, you calculate the moments and shear forces, may be redistributed. You can adjust them, provided that the resulting distribution of moments remains in equilibrium with the applied loads. That is very important. When you redistribute, still the redistributed moments should be able to balance the imposed loads, external applied loads. Now, this requires us to refresh our memory about this idea. There are two terms that sound very similar, but they are different. One is moment distribution. The other one is moment redistribution. I know you have studied these things. Most probably you know the difference, but just for the sake of completeness here, I would like to point out that these are two different things. Moment distribution is a method for analysis of statically indeterminate frames or beams, basically. Okay, you remember how this moment distribution is done, I hope. You take the frame, you say, lock all the joints, don't allow any rotation, and then you calculate what would happen when you apply loads. You find the fixed end moments. But now you take each joint and look at the fixed end moments coming from all the members that are connected. Normally you see that they are not balanced. Therefore, you say, now release that joint. So when you release the joint, that unbalanced moment is distributed among the members that are connected, and then they are carried over to the other end. That causes the other joints also to become unbalanced and so on. So you keep doing this, releasing and locking the joints one at a time, go over all the things and do this several cycles, and then the unbalanced moments become acceptably low, very small values. And then you take that as the final distribution of moments. So that is the idea of moment distribution techniques. This is sometimes called Hardy-Cross method also. That is because this was proposed by Professor Hardy-Cross in UK. At the time, there were no computers, and therefore this became a very popular and versatile method for the analyzing moderately large frames. And even now, this has its use to analyze small frames. And I will show you later, in our designs also, we will make use of the ideas there. But for this same analysis, other methods also are available. For example, you can use slope deflection equations, you can use finite element programs, and so on. So that is, moment distribution is one method available for linear elastic analysis of structures. Whereas moment redistribution is a method for adjustment of moments derived from a structural analysis. Linear elastic structural analysis, you get a certain distribution of bending moments and shear forces, but sometimes the hogging bending moments might be much larger than the sagging bending moments, for example. And then that can cause some problems in the design, because if these are not somewhat equal, then the reinforcement provision can be a bit difficult and complicated and can lead to a lot of congestion. If you have very high hogging moments at the supports, you might need a lot of reinforcement, and then that is not very desirable. So generally in design, we try to adjust these hogging bending moments, adjust them downwards to try to make them manageably smaller. But how do we justify that this requires the structure to be capable of forming plastic hinges and allow rotations at such hinges? That is the idea now. If over a support, if the moment is say 100 and you design the section to be able to carry only 80, what happens is if you start from zero load and if you keep increasing the load, by the time the moment becomes 80, now that has reached its limit. If you try to increase the load anymore, it is going to yield and form a hinge. And if you try to increase the load, it will rotate. But the moment will not increase beyond 80. But due to this rotation, what happens is the load in the adjoining spans will become more and balance the applied load. Therefore, this moment redistribution, if you use it to reduce the hogging moments, it is going to increase the sagging moments in the adjoining span. So there is always a give and take. Now, this is done mostly to facilitate this design. We will see some example in a moment. But remember, moment distribution is one thing. It is a method of analysis. Moment redistribution is adjustment of moments to suit our design requirements. Now, let me take this as an example to show you what will happen in this moment redistribution. Consider this continuous beam, but we assume it to be simply supported for our analysis purposes. So you can analyze this particular case to find the bending moment distribution. You can use moment distribution, you can use slope deflection equations, you can use finite element programs, or whatever. Other methods are also there. But regardless of the method that you use, whether you use moment distribution or slope deflection or finite element programs, you will get the same result because this is the result you get from a linear elastic analysis. So that result might look something like this. Okay. Above this baseline, above the baseline, I am showing hogging moments. Below the baseline, I am showing sagging moments. I am calling these hogging and sagging because otherwise, if you use plus and minus, positive and negative, sometimes it can lead to confusion because there are different sign conventions. Some sign conventions will call sagging moments positive. Some sign convention will use hogging moments positive. So if we don't describe the sign convention properly, using positive and negative can lead to some confusion. So just for this description, I'm saying, okay, hogging moments are plotted above the baseline and sagging moments are plotted below the baseline. So if you just look at this, you can see that the bending moment distribution will be something like this. Zero bending moment at the support at the end. At the other end also bending moment is zero. Then over the support there will be hogging bending moments. And then between these there will be a kind of a parabolic curve due to the uniformly distributed load. Then here also hogging moment over the support, hogging moment over the support, a parabolic, approximately parabolic distribution over the span. And the same here, but the moment here is zero. So when we look at this linear elastic moment distribution, when I say moment distribution, I'm saying meaning the distribution of the moments, not the method of moment distribution. It can be used to do this analysis, but this is the bending moment diagram, let us say, that we get. So what happens is, now we look at that bending moment diagram and say, at B, the hogging bending moment is pretty large. This is going to cause us problems when we try to design the reinforcement. So let us reduce this moment a little bit here. So we decide to reduce the Hoggy moment at B. Okay, bring it down and develop a new bendy moment diagram. So when in the new bendy moment diagram, Hoggy moment at B is reduced by an amount we select. Okay, if it was 100, we say let us make it 80. So we decide that we want to reduce it by 20. And this will be the resultant bendy moment diagram. The black dotted line shows the new bendy moment diagram we get after we reduce the Hoggy bendy moment at B by some amount. We bring it down there. Then this will be the bendy moment diagram. And in the spans far from the adjoining spans, there is no change. Nothing changes here. The only change occurs here. Over the support, you reduce the moment, and then in the adjoining spans, the sagging bending moment will be increased. It will become larger in magnitude. So that is the new redistributed bending moment diagram we have, and we will do our designs for this redistributed bending moment diagram, so that the maximum Hoggy moment will be this value, and the maximum sagging moment most probably will be this value. So we design the reinforcement for those values. So that is the idea of doing the redistribution. I would like you to get a little bit more insight into this idea of redistribution. It is like this. If we look at that same problem, let us direct our attention to this span, the span BC. Let us cut it here and here and take it out. And this is how it looks. And at the left end, there will be some shear force and a bending moment. We call that MB. And the value of MB is in the bending moment diagram. And there is, on the other end, we have bending moment MC. Both I am showing as Hoggy bending moments. And there is going to be a shear force there also to support the distributed load here. So this is the free body diagram for this span BC. Now, if you sketch the bending moment diagram for this one, this is what you get. Here MB, here MC, and then it varies with a parabolic curve due to the uniformly distributed load here. Now, this is the same. This part is what we are looking at, okay? So, this is what we get. Now, a convenient way to look at this particular bending moment diagram is to think of this as a simply supported beam, supported by these shear forces can be thought of as reactions, subjected to two types of loads. One is the end moments, MB and MC. We think of them also as external loads. And the other one is the actual external load, uniformly distributed load here. And now let us show them as two different loads acting on that same structure. So this is the structure, end moments MB and MC acting there. Plus, this is the structure again, the uniformly distributed load acting there, and then you need these vertical shear forces to balance that. So the total load is the sum of these two loads. The technical term we use is superposition. We superpose with this case and this case together to obtain this. Now, when it comes to the bending moment diagrams, these are very simple. If you have MB and MC at the two ends, we can show easily that the bending moment diagram for this case, since there is no the distributed load in the middle, distributed load is 0 in the middle, the bending moment diagram should be a straight line. So at this end we have MB hogging, this end we have MC hogging. You just draw I'm sorry, something happened and I lost my connection, I think. Let me share my screen again. Right. Can you hear me and can you see my screen?
Yes, sir. Yes, sir.
Okay, all right. Thank you very much. I'm sorry about that disruption. So when it comes to this beam loaded by two end moments, the bending moment diagram is very simple. You just draw a straight line to connect the point MB and point MC there. That is the bending moment diagram. It is hogging. Then we look at the other case where there are two reactions at the two ends, which is shear forces, and then there's a uniformly distributed load. So this is like a simply supported beam subjected to a uniformly distributed load. So the bending moment will be a parabolically distributed sagging bending moment. So it will look like this. Now to obtain the combined result of these two, we just have to add these two bending moments. So what we do is, here, we take the first bending moment, hogging bending moment, and we draw that diagram, sketch it. And then the sagging bending moment has to go down from there. So we take this diagram and hang it from this hogging bending moment line. So from using this as the base, we draw this parabolic curve, and that looks like that. So that is how we get this combined bending moment diagram for each span. We consider the two end moments and then the uniformly distributed load in the middle, and this is what we get. So you see, whenever you see a bending moment diagram like this, you have to just think of that as one bending moment diagram resulting from the two end moments, which has a straight line here. And then the second one is the bending moment diagram due to the actual loading on the beam. By the way, we call it the free bending moment diagram. And you just take that and hang it from the hogging bending moment diagram, and you end up with this. And the actual result will be actual result will be this. That will be the remaining part of the addition of these two bending moment diagrams, and that is what we have seen in the previous case. Okay, so always think of the bending moment diagram like that. And now when we want to reduce the bending moment, redistribute, what we do is we make this MB smaller. Okay, so we have brought MB down by some amount, that is the reduction. So this amount is the reduction. We brought it down. And now the new MB is there. At the other end, same MC is there. So when you draw the new bending moment diagram for the distributed loads, it will be this dotted black line. But please note that this does not change. The free bending moment diagram does not change because it has nothing to do with the end moments. It is simply due to the distributed load on the span. Now you take this black dotted line and sketch it there. And take this moment again and hang it from the black dotted line. So that is what you do. So now you see what happened was the change in the bending moments is due to somewhere in the middle, somewhere close to the middle, you have this maximum bending moment, maximum sagging bending moment due to this, which is normally WL squared over 8. So from this red line, you go down by that much, you get the maximum sagging moment. Not exactly at the center, slightly away from the center. But now that the baseline, this red line has become the dotted line, now what happened is, this is the drop. This drop is approximately the same, WL squared over 8. But the change is this amount. That is approximately half of the change. If this change is delta, this change is about delta over 2. So what happens here is this sagging bending moment will go down by about delta over 2. That means the span bending moment will increase approximately by half the value of the redistributed hogging moment. That is the whole idea of this redistribution. The hogging bending moment over the support is reduced by some amount, and the adjoining spans, in the adjoining spans, the sagging bending moment will increase by about half that value. Okay, this is the way to look at how this redistribution works. So this is the same slide that I had earlier. To facilitate the design, we reduce hogging moment at B. Sagging moment in spans will increase by about half this value. Now, again, what is the explanation? This is what is going to happen. If you take this beam, this is the ultimate load. But let us start from zero load. Zero load, the bending moment diagram will be much, much smaller. And if you keep increasing the load, the bending moment diagram will become more and more like this. But the moment here will start from there and slowly go up. If everything was behaving linear elastically, it will end up at there. But if we have designed our beam only to support a moment of this magnitude, okay, we provide reinforcement only to support that magnitude. Then when the bending moment reaches this value, if you try to increase the load, it cannot support that increased hogging moment. The reinforcement is not sufficient. Then it is going to cause the reinforcement to yield and the beam will rotate. Beam will bend plastically. And even if you increase the load further, the bending moment here will remain at the same value, but what will happen is the sagging bending moments will keep increasing as you increase the load. That is how we end up with this black dotted line as the redistributed moment. So please remember that this requires the beam or the slab, whatever strip you are considering, to be able to yield and then bend there, plastically bend. We call that a plastic hinge, okay? That ability must be there in the member to be able to do this redistribution. Now, you might ask the question, how can you justify this? When we do the linear elastic analysis, we say the bending moment is distributed this way. And so if we actually load the beam, it is going to act that way. But now arbitrarily, you are reducing the Haugen bending moment and saying, well, that is okay. How do you justify that? Well, the justification comes from a theorem in theory of plasticity. It is called the lower bound theorem of plasticity. Some of you may have come across this earlier, some of you may not have. But I will give a very, very simple idea about this lower bound theorem of plasticity. This is in my words. Okay, if we can find in the structure a distribution of internal forces and moments, like the bending moment diagram that we show, that satisfies two conditions. One, it is in equilibrium with the external loads. That is, of course, required. Okay, it should be able to balance the external loads. And the second one is, it does not violate yield condition anywhere. Now, it does not violate yield condition anywhere means, if any section has a maximum bending moment it can take, and then after that, it's going to yield. So that maximum bending moment is the yield moment. So not to violate that means, in nowhere, the bending moments in your assumed or in the used distribution of bending moments should not be more than the yield moment at that section. That is what is meant by does not violate yield condition anywhere. The bending moment implied by your the distribution should not be more than the yield moment anywhere. If these two conditions are satisfied, then the collapse load derived from such moment distribution, the distribution of the moments, will be a lower bound of the actual collapse load. What that means is, now with this distribution of bending moments, you find what is the load that will cause the ultimate limit state to be reached. This theorem says, if the distribution of internal forces and moments satisfies this condition, then the collapse load that you find will be only a lower bound of the actual collapse load. Lower bound means it will be either less than or equal to the actual collapse load. Okay, so the redistributed moments that we derived earlier above, it satisfies the conditions A and B. Therefore, the collapse load estimated using the redistributed moment, that is what we use as our design moments, will be less than or equal to the actual collapse load. So with the redistributed moments, if you estimate that the maximum loading that it can take is, say, 100, this theorem says, if you consider the actual structure and load it and consider what will be the final load it can take, it will be more than or equal to 100. The actual collapse load will be more than or equal to the value that you get from your redistributed moment. Therefore, our structure is safe because our redistributed moments will tell us that the maximum load that can be applied there is, say, some value Q, but the actual value is either equal to Q or more than Q. Therefore, our structure is safe. This is the basis of the idea of this redistribution of moments, and many other things that we design rely on this idea, but we don't really say it in our designs very much. But I just mentioned this to explain to you why we can do this almost arbitrary reduction of Hugin moments. There is a certain theoretical justification for that. So we can continue to do redistribution limits. Remember, I told you, for the moment redistribution to work, they should be able to form plastic hinges, yield and allow the beam to bend plastically. So linear elastic analysis with limited redistribution is dealing with that idea in continuous beams or slabs, which are predominantly subject to flexure, mainly bending, have the ratio of the lengths of adjacent spans in the range of 0.5 to 2. If you consider adjacent spans, their ratio should be 1/2 to 2. Redistribution of bending moments may be carried out without explicit check on the rotation capacity. Okay, so we recognized earlier that rotation capacity is required, but this is saying if these two conditions are satisfied, then you do not have to check whether the rotation capacity is there, provided that this happens. Okay, this looks very complicated with K1, K2, etc. Don't worry about that. The values of these parameters K1, K2, etc., are given in the code. But the important thing is this. Delta is the ratio of the redistributed moment to the elastic bending moment. Now, if the elastic bending moment was 100 and we redistributed it to 80, so delta will be the redistributed moment 80 divided by the elastic bending moment 100.8. So that is a 20% redistribution of moment. That should be larger than or equal to K1 plus K2. The other important part is XU over D. XU is the depth of the neutral axis as the ultimate limit state after redistribution. D is the effective depth of the section. Now, in session 2, Professor Priyandayas explained to you about this idea. You have the effective depth of a section, then you have a depth of the neutral axis, that was generally referred to as X. And then this neutral axis depth is limited to some value to allow the steel to yield. I think the value normally used was 0.45. X over D should be limited to 0.45, less than or equal to that. Then we are guaranteed that when you increase the bending moment on a beam or a slab, the steel will yield before the concrete fails. So it will be a ductile failure. When we want rotational capacity also to allow redistribution, these expressions impose further limits on this ratio XU over D. Now, instead of just X, they are using XU, saying that it is the depth of the neutral axis at the ultimate limit state after redistribution. So this XU over D tells you how much of ductility is there in the beam. If XU is very small, then that means the steel will yield, and it will yield a lot, and it can rotate by some amount. So this is the limit that is imposed by EC2. These are the values of K1, K2, etc. EUROCODE recommendation is there. Sri Lanka decision is there. Okay. I think these values are the same as what is given in the UK National Annex. That is fortunate. That is good for us. Why? Because then we can use whatever is recommended in the I-Struct-E manual, which is based on the UK National Annex, in Sri Lankan situations also, because our recommendations are also the same as the UK recommendations. Therefore, we can continue to use the guidance given in the manual published by the Institution of Structural Engineers for our work. I think the Sri Lankan National Annex decided to follow the UK National Annex for this reason also. That is one of the reasons, and the other reason is that in the past we have been using similar approaches from the British standards. So the important thing here is that these inequalities with these coefficients will provide certain limits for XU over D for different levels of redistribution. And if you do the calculations, you will end up with some things like this. Level of redistribution, that is the redistributed, that is delta, okay, redistributed moment divided by the elastic moment. If that is less than or equal to 15%, then the maximum allowable value of XU over D is 0.45, which is the same limit you have if even without redistribution. So even if it is 0, it is 0.45. But if the redistribution is 20%, that is, if you started with an elastic Hooge moment of 100 and you made it 80, you reduce by 20%, then that is delta is 20%, then you must have XU over D limited to 0.4. If the redistribution level is 25%, XU over D should be limited to 0.35. If it is 30%, the limit is 0.3 for XU over D. You can see when the amount of redistribution increases, the amount of rotation capacity also has to increase, and to allow increases in the rotation capacity, the XU has to be made smaller and smaller so that the steel can yield and allow this rotation capacity. There is another factor that comes into play here. By the way, I think I made a mistake earlier. I said this level of redistribution is delta. No, level of redistribution means 1 minus delta. Okay, if you bring 100 down to 80, the delta is 80 divided by 100. But the actual redistribution is 100 minus 80 divided by delta. So that is the level of redistribution. It is equal to 1 minus delta. Okay, I'm sorry about that. Now, there is another factor that affects our ability to redistribute. That is the ductility of the steel. Now, if you keep bending, the steel has to undergo deformations, and that refers to the ductility. How much plastic deformation can our steel undergo before it fails? So in the EC2, they give different classes of steel depending on their ductility. They are referred to as ductility classes. We have not discussed that here, but that is a fairly simple idea. You can go check the EC2. They have this ductility class defined. I think in the I-Struct-E manual also they have given some idea. There are 3 classes, A, B, and C. A is the least ductile, B is next, and C is most ductile. So if the ductility of the steel is limited, then they say the level of redistribution, if you are using class A steel, should be limited to 20%. don't go beyond 20% because the steel might not be able to deform so much plastically. So 20% is the limit if you are using ductility class A steel. If you are using ductility class B or C steel, then you can go up to 30%. Don't go beyond 30%. Therefore, according to this, we have these limits. For ductility class A, meaning that is the lowest ductility class, any steel will be there, satisfy that. You can go up to a redistribution level of 20%. But if you are using more ductile steel, you can go up to 30%. So 30% is the limit. Don't go beyond that, because redistribution, even though in theory we can do it as much as we like, in practice, there are problems because the steel might not be able to deform more than that. So these are the limits that we get from the EC2 guideline. Now we have a small question for you. Okay. Let us say we have a fixed-ended beam here, very simple one. We will take a very simple case. And it is subjected to a uniformly distributed load here. And you know the result here for the fixed end moment is WL squared over 12, I think. And the sagging moment at the middle is WL squared over 24. These are standard values that you already know for a fixed-ended beam. So let us say when we do the linear elastic analysis, the bending moment here comes at 100 and the sagging bending moment is 50. And now we say this 100 fogging moment is a little bit too much for our design because the sagging moment is 50. We would like to kind of balance this. So let us redistribute this 100 to 75. So now we have redistributed this to 75. Since this is now symmetric at the other end also, we do the same and bring that also to 75. Now my question is, what will be the sagging bending moment here after the redistribution? The hogging bending moment is brought down to 75. In the elastic case, the sagging moment was 50, but now what will be the sagging moment in the redistributed case? Right, we have already got a couple of answers. That is very good. One answer is 75, the other answer is 62.5. Any others? Okay, there's 75. So very good. What will be the increase here? 100 is brought down to 75. Right, so there are two suggestions. One says 62.5 and the other one says 75. Okay. Right, good. How do we approach this one? Now, 100 was brought down to 75. So the reduction is 25. So due to this reduction of 25, about half of that will be added to the sagging moment here. So half of that will be 12.5. We already have 50, so the increase 12.5 will make it 62.5. That is the way you have decided on 62.5. But in this particular case, we have done two redistributions. We have redistributed this 100 to 75, and this 100 also has been reduced to 75, because this is symmetric. There's no point doing it on one end and keeping it at the other end. So here also, it has been reduced by 25. Therefore, this is the sum of two redistributions. One, the left-hand side was reduced by 25. That causes the middle sagging moment to reduce by 12.5. The second part is the right-hand side also is redistributed by 25. That also will cause an additional 2.5 to be added to the sagging moment there. That is how the 75 was obtained. So in this particular case, this 75 is the right value. This will be 75. If you got 62.5, don't worry. You have been thinking right, but you forgot that we are doing it twice. Once at the left end, once at the right end. Another simple way is to think that the bending moment 100 and 100 both brought down to 75 and 75. So still you have a horizontal line. And the total depth should be the same as this total depth. This total depth is 100 plus 50, 150. So even if this is at 75, the total depth should be 150. That is the free bending moment diagram depth. So if this is 75, this also should be 75. So there are different ways of looking at this, but I'm happy that you have been thinking right. So that is a good sign that we are following this discussion in a satisfactory way. Right, so this is about redistribution of moments. Mainly Hogging moments are redistributed to make it more manageable when it comes to designs. Right, you must have been thinking, when are we going to discuss designer slabs? We have been talking about analysis so much. This is maybe partly because my background is coming from analysis. I have been mostly doing a lot of my work has been on analysis, but in the last 10 or 15 years, I got involved in the designs also. But okay, that is a small explanation. But I believe that it is important for us to understand these basic ideas about analysis in order to do the design. Right now, we come to design of slabs. I'm saying don't worry too much about it. It is similar to design of beams. A slab can be thought of as a collection of beams. If it is a one-way slab, it is a collection of beams in that direction. If it is a two-way slab, you have two sets of beams. One set of beams going in one direction and the other set of beams going in the other direction. So if you have already studied how to design for flexure in beams, how to design for shear stresses in beams, then slabs is no big deal. It's simply the same kind of design approach applied to this particular type of member. And usually, as I told you earlier, compression reinforcement and shear reinforcement are not required in slabs. So that makes our life even easier. Except perhaps near columns in flat slabs. In flat slabs, near columns, you might develop fairly high shear stresses, which might require you to provide some shear reinforcement. But at this level, we will not go into those aspects. But once you understand the basics, you can go to the code and the manual and follow through that. But for this, we will follow again the guidance provided in the I-Structi manual, because as I told you earlier, the method of analysis given in the EUROCODE general guidelines are the same as the general guidelines used in the I-Structi manual, which combines the guidelines used in the previous BS codes 8110. Therefore, we are justified in following the manual for the design of buildings published by the Institution of Structural Engineers for our work, because it complies with the EC2. We have to consider one-way spanning slabs and two-way spanning slabs on linear support. This is the word that they use in the code. Linear support simply means the straight supports, okay? Nothing to do with something like linear stress-strain relationships and all that. Linear support means it's a straight wall or a straight beam. And we have to consider flat slabs. Guidance, again, idealization of the structure. This is again from the EC2. You can see the sections and the paragraph numbers. The slab is a member for which the minimum panel dimension is not less than 5 times the overall slab thickness. We saw that earlier. This also we saw earlier. If the ratio of the larger side divided by the smaller side in a panel is more than 2, it can be thought of as a one-way slab. If the ratio is less than 2, then we have to think of that as a two-way slab. All this is given in the EC2. Now we come to the I-Structi manual, because that manual has again provided guidance. It has collected the information in the EC2 and provided guidance based on the member type. That is what we are a little more used to. So it has different sections for design of beams, design of slabs, and so on. But the guidance given is, it conforms to the EC2 guidance. So for slabs, they give this, the procedure, the general procedure. Check that the cross-section and cover comply with requirements for fire resistance. Check that cover and concrete grade comply with requirements for durability. We have not discussed them yet. These two aspects will be discussed in the last 2 sessions of this workshop. So don't worry about it yet. But the idea is that when it is time for you to do design, you will know these things. So you will make sure that the cover satisfies, in addition to the requirements to provide necessary strength in flexure and shear, it has to provide necessary fire resistance and durability also. You will discuss that later. But for now, we will look at this. Calculate the bending moments and shear forces, calculate reinforcement, then make a check on span to depth ratios. For flat slabs, check shear around columns and calculate shear reinforcement as necessary. Now, earlier I gave some steps like that. At this stage, I said check for deflections. But in the manual, they give us guidelines that will provide us guidance on the limiting values of span to depth ratios that will ensure that the deflections are acceptable. So we don't need to calculate the deflections and so on. We can follow the guidelines. They are also, they conform to what is given in the EC2 also. So we estimate the span over depth ratio, and that if that is satisfied, that is okay. Then the deflection check is satisfied. You might remember at the very beginning, we showed some values for the span to depth ratios for initial sizing. That also is given in the manual, I-Structi manual. Once again, the manual defines the effective span of a simply supported slab, the effective span of slab continuous over its supports, normally taken as the distance between centers of supports, and effective length of a cantilever slab. All these are defined in the manual, so you can make yourself familiar with those ideas. This is the guide provided in the manual. Basic ratios of span to effective depth for initial design. initial design means at the beginning, before you do any further work, you need to have a thickness. You need to decide on a thickness. So they are saying, use these guidelines to decide on the span divided by effective depth ratio. Then you know the effective depth D. And then if you know what is the cover that you are going to provide, you can find what is the overall thickness of the slab. So this is for initial design. Here you can see if it is simply supported beam, if it is a slab. Normally they don't talk about slabs, simply supported. But one-way or two-way spanning simply supported slab is here. The limiting value of the ratio is 20. So the depth should be span divided by 20. Depth D. So you can come up with the thickness. Then again, for n span of continuous beams, one-way continuous beam, you have these different numbers given. Interior spans of one-way or two-way spanning slabs, 30. So this is only to be used for initial determination of a reasonable thickness. And after that, you will do the calculations. And if that thickness is too much, you can reduce it. If it is too little, you can increase it. But this is for the initial estimate. And then this gives some further notes, further guidance about these values given here. This is the continuation. Say there is notes here, and that notes are here. For two-way spanning slabs supported on beams, the check on the ratio span to effective depth should be carried out on the shorter span. Please remember that, okay? But if it is two-way spanning, you have two span lengths. The span divided by effective depth should be calculated based on the shorter span. But for flat slabs, it's the other way. The longer span should be taken. So these are some small, subtle differences that we must be aware of. Otherwise, we can end up making mistakes. For flange sections with the that is for beams, we flange to rib beam, slabs and so on. We don't worry about that. For members other than flat slab panels, which support partitions liable to be damaged by excessive deflection of the member, and where the span exceeds 7 meters, the table value should be multiplied by 7 divided by span. So span, if span is larger than 7, 7 divided by the span will be less than 1. So the given values will be reduced. That is, if the span is larger than 7 meters, no, if it is a solid slab, not a flat slab. And the requirement is that which support partitions liable to be damaged by excessive deflection. You know, the deflections are decided by considering several things. One is whether partitions are attached to it. And if there is excessive deflections, you might observe that the partitions have got cracks or damages, and that might alarm the users. So that will be a failure in the serviceability limit state. So if you have attached to the floor, if you have partitions that might undergo failure, then you have to be a little bit more careful, and you have to be a little bit more stringent with your deflections. For flat slabs, where the greater span exceeds 8.5 millimeter. Now, for flat slabs, we were told to estimate the span to effective depth ratio, you use the larger span. So if that larger span, the greater span exceeds 8.5 meters, again the same thing. The table value should be multiplied by 8.5 divided by span. Again, if the span is more than 8.5, 8.5 divided by the span will be less than 1. So that value in the table will be reduced a little bit. The values may not be appropriate when the formwork is struck at an early age or when the construction loads exceed the design load. In these cases, the deflection may need to be calculated using advice in specialist literature. Those are exceptional cases we don't have to worry about. We will only consider, for the present, we will only consider normal situations. So now we come to bending moments and shear forces. Slab should be designed to withstand the most unfavorable arrangement, and these are the two arrangements that are recommended. I mentioned these two arrangements earlier. Alternate spans carrying maximum design dead and imposed load 1.35 GK plus 1.5 QK. Other spans carrying only the maximum design dead load 1.35 GK. Or this case, all spans carrying the maximum design dead and imposed load of this much. The moments obtained from elastic analysis may be redistributed up to a maximum of 30%. That is what we discussed earlier. Redistribution can be done up to a maximum of 30%, except for plain or indented fabric, for which the limit is 15%. We are not talking about these things. So this again tells us the maximum redistribution level is 30%. That also, if you are using steel of ductility class B and C. If you are using steel of smaller ductility, class A, then you are limited to 20%. Okay, the Sri Lanka National Annex has prescribed additional arrangements of loads, but don't worry about that. One-way spanning slabs. For continuous slabs with a substantially uniform loading, these are conditions. Okay, A, substantially uniform loading. B, dead load greater than or equal to imposed load. And at least 3 spans that do not differ by more than 15%. That do not differ meaning that their length should not differ by more than 15%, almost equal spans. If these conditions are satisfied, the bending moments and shear forces may be calculated using the coefficients given in table 5.2. Now, these conditions are not very difficult because for most buildings that we deal with that have a regular arrangement of beams and columns, all these conditions will be satisfied so that we can use the coefficients from here. This is what you are used to. If you are familiar with the earlier BS codes, you will remember that this sort of tables were given there also. So I-Structure manual also has more or less reproduced the same or similar tables. So bending moments and shear forces for one-way slabs. Moment shear if it is simple supports and if it is continuous. Then the moment and shear are given here. Simple end support, moment is 0. Shear force is 0.4 times F. What is F? F is the total design ultimate load for each span. Now, I want you to be very, very careful here. What we are saying is that F is if you consider each span, now this is a continuous beam that has several spans. But if you consider a single span, we are talking about the total load on that span. And also, please remember that this given value 1.35 GK plus 1.5 QK, if you are using GK and QK as newtons per meter squared or kilonewtons per meter squared, like what was given in the table for imposed loads, now you have to make sure that this, to find the total load, this is per unit area, and we are considering a unit width of a strip. In that case, this should be multiplied by the length of the span. So this expression 1.35 GK plus 1.5 QK is correct if you mean by GK the total dead load on the span, and by QK the total imposed load on the span, not per meter square. So please be very careful, okay? F is the total design ultimate load on that span. In that case, the shear force will be 0.4 F, and if when continuous, it is end support. If it is a continuous, there is some continuity at the ends. End support, there is a moment also, 0.04 FL. L is the span length, and shear force is 0.46 F. And in the end span, in the middle, there is a moment, saggy moment of this much. Now here, note that they are using minus and plus to indicate the bendy moments. As I told you earlier, this can lead to confusion if you are not sure about the sign convention that we use. But here we can see what the sign convention is. Over the supports, say interior supports, they say the moment is minus something. So that means over the interior supports, the moment will be hogging. So if it is minus, that means the sign convention they are using here is hogging is negative, sagging is positive. So please understand that. If you think in these terms of hogging and sagging, that will be much easier rather than this plus and minus. But these are the moments and the shear forces at different places. Now, what is penultimate support? Penultimate means one before the last. Okay, so if you have a continuous slab, the last support is there, and that is this end support. And the support next to the last support is what is called the penultimate support. Sometimes these words can be a problem for us. Okay, there is a question in the chat. At support, F and L are considering for conservative, meaning in a conservative way, we have to consider F and L. Are we doing that? Because of two different span at two sides near a support. Okay. So the question is, now we say this is applicable at least three spans that do not differ by more than 15%. But it is possible for them to differ by 15%, the length. So if one span is, say, length is 5 meters, then the next span can have a length 5 into 1.15. So there can be a difference in the length. Now, what do we use for F and L in such cases where the span length changes? Very good question. That is something that will come to all of us when we try to use this table. So the idea is that if you are considering middle of the span, okay, interior spans, in the span, it is the sagging moment. So there is no question, you have to use the F and L for that span. That is okay. Okay, so in the interior spans, there is no problem. You use the value for the particular span. So F and L will be different for different spans within these limits. But when the spans are different, you might end up with a situation where adjoining spans have different lengths. And now what do we do? So don't worry about that also. Let me get a new slide here to do that explanation. Okay, we got a new slide. I can. Right, so let us say we have two spans, two adjoining spans, but the length here is L1 and the length here is L2. Therefore, the total load F here will be F1, the total load here will be F2. These are two different values. Now, we need several things. One is we need the bending moment here and the bending moment there. Now, for that, the given coefficients can be used without any problem, because for this bending moment, and the value of L1 and F1 will apply. For this bending moment, the value of L2 and F2 will apply. That is not a problem. But what about the shear forces? Once again, when you are talking about the shear force, we try to see what is the span that contributes to the shear force. So if we are talking about the shear force here, that will be L1 and F1. Similarly, the shear force here will be using L1 and F1. But the shear force there will use L2 and F2. Okay. Similarly, when you are looking at the bending moment, if you are looking at the bending moment over the support here, it will use L1 and F1. Bending moment here will use L1 and F1, but the bending moment there will use L2 and F2. Okay, so the first rule is we should use the parameter L and F associated with the span that contributes to the values. But then you will have a problem where you might have a bending moment diagram, say over the support here. The bending moment diagram will be that. But on the other side, the bending moment diagram might be that, because the bending moment calculated using L1 and F1 from here will have that value, and the bending moment calculated using L2 and F2 from here will have a different value. Now, what do we do? So, what we do in these cases is, again, we do something like our moment distribution. Okay, now we are saying that here there is an unbalanced moment, but over a support you can't have an unbalanced moment. So we redistribute this to bring it to the middle. So this is reduced by some amount, this is increased by some amount, so that we get the mean value of the two bending moments. And that is what we can design this for. But we must remember that when we reduce this, the mid-span moment also will change a little bit. Here also the mid-span moment will change, but it will change upwards, so you don't have to worry too much about it. Okay, this is one way to handle that. Is that does that explain the situation? I mean, how to handle this? Now, I can give some further information also. Now, if you are using moment distribution to do this, you release that and distribute the moments. Part of that moment will go here to reduce, part of that moment will go on this side to increase. But here I am saying use 1/2 on the left-hand side, 1/2 on the right-hand side. That is because the lengths involved here, L1 and L2, are approximately the same. Okay, so when you do moment distribution, normally the moments are distributed in proportion to the stiffness. Stiffness will be L over, 4EI over K is 4EI over L. But for a slab, both these will be constant, so the moments will be distributed proportional to 1 over the length. So if L1 and L2 are different, it will not come out as exactly 1/2. But I'm saying L1 and L2 are approximately equal. The difference is only 15%. Therefore, we can approximate this as a 1/2 and 1/2 division. So we come to the middle value there for the bending moments. For the shear forces also, you can treat the shear forces separately on the two sides. That is possible, but the bending moment you have to use one value. Therefore, use this average of the two bending moments. Okay, does that clarify the situation for you? The participant who asked that question? Okay, all right. Now, this is very good thinking, okay? This is what we should be doing in these workshops. There is another suggestion. We can go for the maximum value when length difference is within 15%. Yeah, that is possible. That says if you calculate two values at the support, use the larger value. That is a conservative approach. That is perfectly all right. But you will be using slightly more reinforcement. But sometimes you might not need more reinforcement because reinforcement doesn't change continuously, it goes in steps. So you might be able to manage the same reinforcement, but that is okay. That is a very conservative approach. But that is fine because the changes are going to be very small because the lengths are only different by 15%. Therefore, that suggestion also is fine. See, once again, as the designer, you have the freedom to decide which of these two methods to use, for example. Both are okay, but you should be able to justify what you have done. That is the important thing. If there is any question, For example, if there is some inquiry, there is some legal case, and they want to know how did you do this, you should be able to clearly say, this is what we did, this is the justification. Fine, okay? Right, so this is how you can find the bending moments and shear forces for a one-way spanning slab. Fairly straightforward. We use the table given in the manual. There is a very important statement here also. Okay, allowance has been made in the coefficients in table 5.2 for 20% redistribution of moment. So the values that are given here are already redistributed by up to 20%. Please remember that. You can't do any more redistribution. You are not supposed to redistribute the values you get from here. Now you will ask, what we discussed earlier, was that a redistribution? No, that is not a redistribution. It is a normal elastic analysis where we have distributed, moment distribution has been used. It did not redistribute the moments. Okay, so this redistribution of 20%, remember, when we use these coefficients, already a redistribution of 20% has been done. That will become important when we come to designing the reinforcement. Right, now we come to the case of two-way spanning slabs on, again, linear supports, which means straight beams or walls. So here also, the EC2 does not give us any further guidance. It gives the general principles to be used in linear elastic analysis. But fortunately, they are the same as what is used in the previous British standard. So iStructy manual has provided further information that we can use to find the bending moments. Coefficients are given. So bending moments per unit width. Okay, please remember that it is provided for a unit width. Now I must say here also, the easiest thing to do is to consider a unit width. If you want, you can use other widths for this strip also, one-way spanning slab. But then when you come to calculating F is the total design ultimate load, you have to consider the width. If you consider unit width, it doesn't change your numbers. But if the width is only 0.8 meters, and if you use the width as 0.8 meter strip, then when you calculate F, you have to incorporate that also. In the two-way spanning slabs, there is no question like that. They are providing the values for bending moments per unit width, MSX and MSY, in the two directions for various edge conditions. I'll show you what MSX and MSY in a moment. And the values are MSX equals beta SX times N times LX squared. And MSY is beta SY times N LX squared. Please note that even though the subscript is for X direction and Y direction here, this length is the same, LX and LX. LX is the shorter span. So Ly is the longer span. In this expression, this refers to the shorter span in both cases. Even though we are talking about bending moments in the two directions, this Lx is the same. Okay, please remember that. N is the total design ultimate load per unit area, which is given by 1.35 GK plus 1.5 QK. Now, they are still using capital G and capital Q here. That is causing some confusion if you are not careful. Normally, what we would write this, what we would use here is simple G and simple Q. So if we were to write this, I would write this as 1.35 simple GK plus 1.5 simple QK. Because the simple G and simple Q refer to the load per unit area. Normally, the capital G and capital Q is used to show the total load. But here there is this little confusion with the notation, but we must understand what this means. But they say this is per unit area. Because you remember in the EN 1991, where they gave loads, they showed the values under simple QK. The imposed loads were given as simple QK. That is because they were given per unit area. But those are minor things that nevertheless we must be aware of. So the requirement is that if we can find beta Sx and beta Sy, we can find MSX and MSY. This is how we define MSX and MSY. This is the span, shorter span Lx. This is the longer span Ly. So the table is provided for a unit width strip. So this strip, say it has a unit width. And the bending moments that will occur in the strip like this, where the strip direction is X, and that is the direction of the spanning direction for that strip. The loads are going from middle to that edge and this edge, they span in the X direction. That is MSX. In the other direction, you have MSY. That is on a strip aligned in the Y direction. So we need to carefully understand these definitions for us to be effectively using these tables. And this is for a two-way slab. That means Ly divided by Lx should be less than 2. If it is more than 2, it becomes a one-way spanning slab. So only this MSX will be there. Those coefficients were given previously. Now, these are the coefficients that are given. Once again, this is an extract from the I-Structi manual. Actually, I-Structi manual did not come up with this table. This table has been used previously also. These are simply the result of elastic analysis on this type of slabs. So, short span coefficient beta Sx. Remember, for the short span, we need MSX. So, MSX is beta Sx times NLx squared. N is the load, Lx is the shorter span. So, NLx squared is a constant value. Beta Sx changes. So, here, short span coefficient beta Sx for different values of Ly over Lx. So here, this is the value Ly over Lx equals 1. That means a square panel. At the other end, we have Ly over Lx is equal to 2. That is the limit of two-way spanning. In between, we have different values. And if it is an interior panel, negative moment at continuous edge. So if it is an interior panel, what we are saying is that we have an interior panel like that, where there are adjoining panels all the way around. So if you consider your strip in the X direction like that, here there is going to be a negative moment on a section like that. And there is going to be a negative moment here also. And then there is going to be a saggy moment in the middle. So that is what they mean when they say negative moment at continuous edge. So the coefficient is here for different values of Lx, Ly over Lx. And positive moment at midspan, the coefficients are given. Then long span coefficient beta Sy, that is bending moments along this y direction, a strip along the y direction. That MSY is beta Sy NLx squared. But they say that does not change very much with Ly over Lx. So they give one value for all ratios of Ly over Lx. All ratios meaning Ly over Lx can change from 1 to 2. Within that value, the beta Sy is the same. So for all ratios, all aspect ratios, you use the same value. And then you have other condition. One short edge discontinuous. That means it stops. One short edge is the end. There's nothing beyond that. Then this table continues. 3, 1 long edge discontinuous. 2 adjacent edges discontinuous. These are all the different possibilities that we can get. So from this table, you can get the values of beta Sx and beta Sy. And with that, you can find what is the bending moment per unit width acting in the slab. Bending moments per unit width. And then you can do the design for the bending. Now we need the shear forces also. Here they have made our life quite simple by saying no need to use very complicated calculations to find the shear forces and shear stresses. Just use this load distribution scheme. The distribution of the reactions of two-way slabs onto their supports can be derived from figure 5.2. Now they say the distribution of the reaction. Sometimes when it says reactions, we think of just a single reactive force. No. Here this is a distributed reaction. The distribution of the reaction of two-way slabs onto their support. So there is a support here, and the reaction is distributed over that support. So what is that value? We just think of the load transfer this way. You draw these diagonal lines at 45-degree angles, and they meet there, and then you connect them this way. And then you have this trapezoidal area here. The load from that trapezoidal area will go to this edge. So to find the shear force per unit length there, all you have to do is consider a unit strip there and find the total load on this unit strip, and that will be transferred to the wall there as a reaction. So that will be the reaction per unit length. And you can see that over this part, the reaction, which is actually the shear force at this end, shear force will be uniform. But from there, it will reduce to 0 at this end. So if you are doing your design, you will use this value and use that for the entire length, even though we know that towards the end it reduces. Similarly, for the other side, you can consider a unit strip here and calculate the total load, and that will be the shear force there. So it is fairly easy and simple to calculate these shear forces in slabs, two-way slabs. There are some notes here. Note what are they saying? The reactions shown apply when all edges are continuous or discontinuous. If the conditions on all four sides is the same, continuous or discontinuous, this kind of distribution applies. But when one edge is discontinuous, the reactions on all continuous edges should be increased by 10%, and the reaction on the discontinuous edge may be reduced by 20%. So, for example, if this edge is discontinuous, if it ends there, then you calculate the normal way, but on the other three sides, you increase the values by 10%. And over here, you can, if you want, reduce the values by 20% to find the reactions that will come on the support, the wall or the beam. You can do that. Okay, discontinuous means there is a beam or wall, but joining that there is no slab. On the other sides, they are continuous. When adjacent edges are discontinuous, the reaction should be adjusted for elastic shear considering each span separately. So if two of these are discontinuous, then you have to consider that as a special case, and using your linear elastic theories, you can obtain the shear forces on the two edges. But if you look around, there will be standard solutions for those also. So finding bending moments and shear forces for two-way spanning slabs is not very complicated because we don't have to do any further calculations. But there are certain restrictions. Okay, the restrictions are not given here. I think there are some restrictions. Okay, now this is about I want to point out here again a problem that we discussed earlier can show up here also. What is that problem? If we have unequal spans on adjoining slabs, okay, let us say we have something like this, but these lengths are different. This length and this length is different. So when you use these coefficients and calculate the bending moments, on this side you will have one bending moment, on this side you will have a different bending moment. So what do we do now? I think you know the answer because we discussed okay, here is a comment about our previous table. In BS, we had table 3.15, I think 3.15 for this calculation. Yes, even the table that we have reproduced here from the manual is very similar to these tables we had in the previous BS codes. EC2 has omitted that. Why is that? I think there's a question mark. Why is that? That is what Narayanan and BB meant when they said that EC2 gives limited guidance on linear elastic analysis. What they say is that we will assume that the design engineers are competent structural engineers who will be able to do these calculations themselves. That is one way to look at it. But they give general guidance on how to do the linear elastic analysis. So if you follow those guidelines, you can do the calculations and end up with the same tables, similar tables. But they are not going to that extent because that will be a little bit too restrictive. Everyone has to use that. But that is not the case. If you want to be trying to save every rupee or every dollar in your structure, you might not use these tables at all. You might use a finite element program to analyze these slabs and find the actual moments that develop there, because the values given are kind of conservative. But if you do the actual analysis using finite elements, you will get a more reliable values that are suitable for the particular panel dimensions you have. Even a 15% change in the panels can result in some change in the moments. So the code is saying you can do that if you like, if you are competent to do that, please do that. We have no objections. No need to use the coefficients given in the tables. Okay, I think that is what we do. And also please remember that if you do a computer analysis, finite element analysis with all the spans loaded, all the panels loaded, you can still do some redistribution that is allowed. Okay, so that is my explanation for that question. Why doesn't EC2 give these tables? Another one, maybe EC2 wants us to do more work. No, that is not true. I'm just kidding. EC2 wants to give more flexibility and more responsibility to the structural engineers so that they will try their best to produce the best designs by trying to get the maximum out of the material that they use. Okay, all right. So I come back to the problem that we might encounter if we use these coefficients given in the tables. You will have M1 on one side, M2 on the other side. From one panel, you will get M1. From the other panel, you will get M2. And this M1 and M2 are different. So what do? This is the same question that we handled earlier. If on two spans, adjoining spans, the values are different, we came up with two possibilities. One is be conservative and use the larger of the two values. There is a Hoggy moment M1 on one side, Hoggy moment M2 on the other side. Is M1 is larger, then you design that section for M1. It will be able to handle M2 also. So there's no problem. That is one way. Or if you want to go a little bit further, you can do a moment distribution by assuming that the moment here is distributed between the two sides in proportion to 1 over L1 and 1 over L2. So if L1 and L2 are substantially different, these values will also be different. So instead of going half and half, maybe 60% will go to one side, 40% will go to the other side, and so on. But those calculations can be done if you want to go to that extent. Otherwise, you can even go half and half. If the lengths are not very different, if the panel lengths are not very different from one another, you will still be okay. Okay, so that is something that can come up at some point. Right. So we realize that handling two-way spanning slabs are not very complicated. Fortunately for us, there is this guidance given in the I-structure manual, and we can quickly do our job. Now we come to flat slabs and try to see how can we find the bending moments and shear forces in flat slabs. So once again, some guidance is provided in EC2. For example, section 9, subsection 9.4, flat slabs. But more details are required for a design to do the calculation. Such detailed guidance is provided in handbooks, for example, in I-structure manual. We are going to discuss here the extracts from I-structure manual. Now, the I-structure manual recommends the subdivision of the slab into column strips and middle strips, as shown in figure 4.2. So now we are looking at a portion of a flat slab. These are 4 columns and that are supporting part of the set of columns supporting this flat slab. So in order to analyze this, to find bending moments and shear forces, there are these approximate analytical methods proposed in the earlier codes also. BS 8110 did that, and the manual also gives that. And in this case, there is an annex in the EN 1992-1-1, Annex I, that also provides very similar guidance. So they all agree on this guidance. However, this Annex 1 is indicated not as a compulsory part. It's not a norm, but it's informative. It is only for information. It's not a norm, it's not a standard. So once again, it is providing some flexibility to the designer. They are saying this is one way to do it. So that one way given by the manual, I-structure manual, and BS 8110 from earlier times, and the EN 1992, all are very similar, and this is the idea. If you consider a strip bounded by these lines that pass, center lines passing through the columns, this whole strip is a typical strip for this flat slab. When there are many rows and columns of these columns, you can subdivide your flat slab into several this type of strips. And to analyze, they say subdivide the strip into a middle strip here and column strips. And note that from the other adjoining span also, a column strip will come. So the column strip will be this part plus this part coming from the adjoining slab. So the column strip width will be, total width will be this. And this is the middle strip. And here again, there's a column strip. So that is the strip going this way. That is how you divide them. And the distances, lengths are given. LX is shorter span, the distance between these two columns. So you divide that into the middle strip and the two column strips this way. Just take 1/2 of the width and assign it to the middle strip, place it symmetrically, and then 1/4 goes to the column strip and the other quarter goes to the other column strip. And you do that for the adjoining one also. So there will be another column strip of Lx over 4 coming here. Together they will also be Lx over 2 if you have the same Lx. Otherwise there will be a small difference. But the main idea is subdivide your strip in the flat slab into column strips and middle strip. And do the same in the other direction also. So if you consider this direction, this is the longer span, the distance between the columns this way. And once again, subdivide it into a middle strip and column strips. And the width of the column strip is the same as this Lx over 4. Please note that, okay, this is Lx over 4, not Ly over 4. It is still Lx over 4, the same as this one. So this side also you will have Lx over 4. What remains is the middle strip. So that will be Ly minus Lx over 4 minus Lx over 4. That is Lx over 2. So the width of the middle strip this time is Ly minus Lx over 2. That is the small difference between the short span and the long span. In the short span, the middle strip is just 1/2 of the short span. And the column strip, part of the column strip is Lx over 4 and Lx over 4. But here, in the other direction, the column strip is the same Lx over 4. Therefore, what remains is the middle strip Ly minus Lx over 2. However, the main important idea is the division of this into these strips, because when these are loaded, for example, the loads will be mostly transferred. Now, there is going to be loads everywhere on the flat slab, but those loads will be transferred to the columns to be transferred downwards. So how does that happen? By these strips bending. There is no firm division in the physical strip, but we imagine, we idealize that is what is going to happen. So in this direction, the column strip is going to bend and it will be supported by the columns. And here in the middle strip also is going to bend, but not as much as this, because the columns are a little further away from the middle strip. So there will be some hogging moment there, but not as much as in the column strip. But the whole idea is that when you consider the entire strip, the bending moments that appear over the column here, and over the midspan, when you add all of them together, it should be equal to the total bending moment required for that strip. But the proportions are different. They are given in our code. They say a certain percentage of that should be carried by the column strip. A certain proportion should be carried by the middle strip. So that guidance, if a flat slab has at least 3 spans or bays in each direction, and the ratio of the longest span to the shortest does not exceed 1.2, the maximum values of the bending moments and shear forces in each direction may be obtained from table 5.4. And again, this assumes 20% redistribution of bending moments. Okay. Keep this in mind. The values given here have already been redistributed, so we can't redistribute them any further. They also say if these conditions are not applicable, that means if flat slab has at least 3 spans or bays in each direction, and the ratio of the longest span to the shortest does not exceed 1.2. So if it exceeds 1.2, these tables cannot be used. So in that case, what do? The bending moments and shear forces may be determined using frame analysis or other similar methods or finite element methods. Manual gives a little bit more details. Frame analysis means you think of this strip that continues further to the sides as being supported by some support at these column locations. So it will become a strip with supports, and those supports, if you like, can be made columns so that there will be continuity at the joints, and then the columns also will be able to take some moments, and the strip also will be able to take some moment. That becomes a frame. You can analyze that using moment distribution, slope deflection, or computers. Computers is the most obvious choice, I think. Then the division of panels, except in the region of edge and corner columns. In the edges and corner columns, things are slightly different. I'm not going to go into those details. You can look them up yourself in the manual, but we will consider the general interior panels. Flat slab panels should be assumed to be divided into column strips and middle strips. See figure 4.2, that is the figure we saw. In the assessment of the width of the column and middle strips, drops should be ignored if their smaller dimension is less than 1/3 of the smaller dimension of the panel. Now, this brings us to this idea of drops in the flat slabs. I am sure you are aware of them more so than I am. So normally, if we have a flat slab and if there is a column, this is the general idea that we have been looking at so far. But sometimes the shear stresses that develop in the slab, when you have this small area of the column applying this large reaction, might be a little more than what the slab can handle, even with reinforcement. In that case, what we do, sometimes we have a flared column head, something like that, kind of a conical part around the column, so that the shear forces now will be here and the perimeter will be larger and the shear stresses will be smaller. This is one way. The other way is to have a column head like that. That also serves the same purpose. Okay, so what this says is that in the division of panels, the width of the column and middle strips, when you find them, drops are those what we showed now. Drops should be ignored if their smaller dimension is less than 1/3 of the smaller dimension of the panel, which means if the column heads are small, don't worry about them when you decide on the column strip and middle strip. But if they are larger than this limit, then you will have to take them into account. We will not go into details there, but again, this manual gives guidance on that. In such cases, sometimes you limit the column strip to the width of the column head and consider that as the column strip, and that will very often that will make the middle strip wider. But the general plan, method used will be the same. now I have been going on with this description for quite some time. I am supposed to have another break. We wanted to have at least 2 breaks. I think we had only 1 break, but now there is only another 20 minutes to go. So I beg your pardon I forgot that we need to have another break here. But I assume that you will forgive me if I do not have a break at this point, because there's only another 20 minutes remaining in our time slot. Okay, I'm sorry that I forgot the second break. So this one says, don't worry about column heads. If they are small, you just divide the slab into column strips and a middle strip. And then it gives us guidance on the bending moments and shear force coefficients for flat slab panels of 3 or more equal spans. See, it is 3 or more equal spans now. So if the span lengths are different, we can't use this. But once again, we have to be a little bit practical, okay? When this is more 3 or more equal spans, I will interpret that to say if the spans do not differ by more than 15%, that should be okay. Because equal, there should be a certain tolerance. But if we are not sure, if you want to be more accurate, you will have to do a frame analysis using classical methods or computers and so on. So for the time being, we will say approximately equal spans. These are the moment, shear, and column moments. This time, we are not assuming that the columns are simple supports. We are saying columns are rigidly, the columns and the slab form a rigid joint, so that if the slab rotates by some amount, the column also will rotate, so that the column also will take some moment at the joint. So the column also has a certain part to play in the in deriving the values of the moments. So that is why we have the moment, shear force, and total column moments. So at a outer support, the near middle of end span, at first interior support, at middle of interior spans, at internal supports. All these are for the entire strip that goes from one end of the flat slab to the other end. There can be several spans, and there can be that corresponding number of column supports. So these values are for the entire typical strip. That typical strip consists of the middle strip and the 2 portions of column strip. So, for example, if you look at the moment, at middle of interior span, there is a moment given by this much. But this is the moment carried by the entire strip, which means it is the moment carried by the middle strip and the column strip together, not the moment carried by each of the 2, middle strip and column strip. This is the total moment in this table. That is what we get. The shear forces and the moments are given for the total width. And then there are some notes. F is the total design ultimate load. Once again, please note that this F refers to the total load on a span. So now this time the span has the width equal to the width of the strip plus length equal to the span, and that area is loaded by this load. So you have to be very careful when you calculate F. When it says total load, you have to consider the area of the strip on which the load is acting. These moments may have to be reduced to be consistent with the capacity to transfer moments to the columns. The midspan moment C must then be increased correspondingly. What this says is that there is a certain limit to the moment that can be transferred to the column. You can't transfer a very large moment. And the values are given in the manual, the maximum moment that can be transferred to a column. So if the total column moment that you calculate here comes up to be more than that, you have to say, no, it can't be more than that, it has to be reduced. And then the moment carried by the other parts will have to be adjusted accordingly. Okay, and then the midspan moments also will be changed slightly due to that. The total column moment should be distributed equally between the columns above and below. Now, if we are talking about floors, flat slabs that serve as floors, there will be a column above the flat slab and there will be a column before the flat slab. So the slab is connected to two columns, above it and below it. So in this table, they give the column moments, that is the moment contributed by both columns on the top and the bottom. So as a simple approximation, the total column moment should be distributed equally between the columns above and below. Now, even though they don't say this explicitly, this divide equally between the columns above and below simply makes an assumption that the height of the columns below and height of the columns above are approximately the same. If you have very different heights, then you will have to do a small analysis to find how much of the moment will go to the top column and how much of it will go to the bottom column. Moments at supports may be reduced by 0.15 F HC, where HC is the effective diameter of the column or column head. Now, once again, the idea is this. When you find the bending moments with some linear analysis, you will be finding the bending moment at the center line. But actually what you need is this. So the bending moment will be reduced a little bit when you come some distance from the center line of the column. So if you like to work at the very limit, you can allow for this small reduction. That is what this note means. Okay, moments at supports may be reduced by 0.15 FHC, where HC is the effective diameter of the column or column head. Now, if you have a square column, what does this HC mean? It is the effective diameter, which is basically the diameter of a circle that will have the same area as the column. If the column is square or rectangle, you will find that effective diameter that way. Okay, so this gives the total shear forces and bending moments carried by the entire strip. But we have divided the entire strip into two strips, middle strip and column strips. So the next table gives us how to distribute these design moments between the strips. The design moment obtained from analysis of the frames or from table 5.4 should be divided between the columns and middle strips in the proportions given in table 5.5. These are the proportions. So, design moment, negative. Negative means it is hogging moment over the support. Column strip percentage is 75, middle strip percentage is 25. So, of the hogging moment that will develop along the line connecting the columns, 75% of that will be carried by the column strip. That is reasonable, right? The middle strip does not have support, so it will carry only 25% of that. When you add these two numbers, you should get 100, because 100% of the negative moment should be carried, but 75% is carried by the column strip and 25 is carried by the middle strip. Positive values, those are the sagging bending moments in the middle between the columns. Their distribution is coming closer to being equally distributed because there are no columns to help there, but still the column strip carries more and the middle strip carries less. 55% for the column strip and 45% for the middle strip. There is a question here. How do we, in the chat box, there is a question. How do we distribute the load between short and long spans? That is also a very good question. I also was thinking on this question some time ago, and I was trying to find the answer. There is no division like that. We have subdivided the slab in both directions. Okay, so we have strips going in this direction and we have strips going in the other direction. So we just use this analysis in both directions. You analyze the strip going in this direction using this method, and you analyze the strip going in the other direction also using the same method. And that is how you get the different bending moments and shear forces in the two directions. There is no division of the loads. You just use the same load for each of the two directions. Okay, if you consider the load, the strip this way, you will get bending moments on sections perpendicular to that. If you consider the strip in this direction, you will get bending moments on sections perpendicular to that. So this will give different bending moments on two mutually perpendicular planes. Right, so the sagging bending moment or the positive bending moment has to be divided between the column strip and the middle strip in this proportion: 55% to the column strip, 45% to the middle strip. Then there's a note for the case where the width of the column strip is taken as equal to that of the drop. Okay, I told you if the drop is large, then you take the column strip to be the same width as the drop, so that the drop also can be a part of the column strip. The design moments to be resisted by the middle strip should be increased in proportion to its increased width, because if the new width of the column strip is smaller, the length of the width of the middle strip will be larger. So what they say is these percentages will have to be increased in proportion to the increased width. But the moment, the contribution on the column strip also will have to be changed. Make sure that the total positive and total negative design moments resisted by the column strip and middle strip together are unchanged. Here, it should add up to 100%. Similarly, even if you change the amount that goes to the middle strip, the amount that goes to the column strip also should be adjusted to make everything equal to 100%. Right, now the main important part is over. We have now seen how we can estimate the bending moments and shear forces on single one-way spanning slabs, two-way spanning slabs, and flat slabs. Now we have to do is decide on the reinforcement. But we know how to do that. We discussed that in session 2 and session 3 for flexure and shear, how to do that. Only thing is, make sure that the value of D appropriate to the direction of reinforcement is used, because when you have reinforcement going in two directions, the D for one layer will be different from the D for the other layer. So when you are doing the calculations, make sure that you use the correct value. Take into account the extent of moment redistribution used in estimating the moments and shear forces. Remember, I told you in most of those tables, they said 20% redistribution was done. So we have to keep that in mind. You will see why in a moment. Then check whether shear reinforcement is required or not. Usually, shear reinforcement is not practical in slabs with thickness less than 200 millimeters, because if you have to provide shear reinforcement, this is the way you will have to do it. But if this thickness is 200 millimeters, it is going to be very difficult to make this arrangement, and it is very difficult to make sure that these become effective. So they might not be able to act as shear reinforcement. Therefore, for slabs with thickness less than 200 millimeters, we don't provide shear reinforcement, because that will not be effective. Now, to calculate the reinforcement, all you have to do is you find the maximum bending moment for bending moments. You find first the maximum bending moment that the section can carry. That is equal to this K limit FCK BD squared. You saw that earlier. In earlier work, you saw that K limit is 0.167, I think. But here, depending on the amount of redistribution, that can change. And then if the applied moment is less than the mu, then single reinforcement is enough. And then this tells you how much, how much tension steel is required. M over 0.87 Fy. Z is the lever arm, but this Z, you know how to do the calculations, but there is a convenient table that we can use, convenient graph that we can use to find Z. So this graph is produced using this stress block and the analysis that you discussed in session 2. This is the graph given in the manual. Here on the vertical side, it gives the values of Z over D. Here, there is a scale that gives the value of X over D. Then in the horizontal axis, you have M divided by BD squared FCK. M is the moment that you have acting on that section. So K is M over BD squared FCK. So that will be somewhere along this line. And then there is this limit of graph for various percent of moment redistribution. Remember, I showed you a little table earlier saying that X over D is limited when there is redistribution. So here what is happening is, if the redistribution level is 30%, this is the value, the limiting value. And the value of K limiting value is 0.120. If it is 25%, this is the limit. And if it is 20%, this is the limit. So mu is dependent on this limiting value of K. This is called K limit. And that is the mu that you have to calculate. So depending on the value of m over bd squared, you will find the K. These are the limits. So you should not go past that. If you have 30% redistribution, you should stop here. Don't go beyond that. 25% here, 20% here, and so on. And now from these lines, this line is for x over d, this line. If you have calculated K, from there you can extend this and find the value of x over d. And this line gives z over d. And so if you extend it all the way there, that will give z over d. X over d is read from the right-hand side. Z over d is read from the left-hand side. So for any value of K, you can find Z. Once you find Z, you can find the steel area required. So that is all there is to flexural design. Then we come to the shear. It should be noted that for slabs less than 200 millimeter thick, shear reinforcement is not effective. Solid single-way and two-way slabs, shear reinforcement is not normally required, provided the design ultimate shear force VED does not exceed VRDC. You know these symbols. We discussed that in last Saturday when Dr. Yapa was discussing shear forces. These are the expressions that we had there. So they are not new to you. And this is why this is not effective. Okay, the shear reinforcement, if this thickness is 200, it's going to be difficult to work with. Now, detailing of reinforcement in slabs. Right now, the shear force for solid single-way and two-way slabs, you find the shear force per unit length here, VED, and check whether it is less than or equal to VRDC. Normally that happens. If that is the case, then no shear reinforcement is required. If it is more than that, then you have to provide shear reinforcement. But if the slab thickness is 200, that is going to be difficult. So you might have to make some changes. Either change the slab thickness. If you increase the slab thickness, you might be able to satisfy this condition and so on. Now, detailing of reinforcement, how to distribute the reinforcement. EC2 does not provide a lot of guidance, but it provides some guidance about how to curtail reinforcing steel. You have not discussed that yet, but Dr. Yapa said he will discuss it next time. But that is only to show how to curtail a single steel rod. But if when you have a lot of them, it is not very practical to do it for different reinforcing rods differently. So it is good if we have general simplified rules, but EC2 does not give such rules. But the earlier code BS 8110 gave simplified rules. In the textbook, this mostly Bungi and the other third author, they have suggested that since the guidelines are the same, curtailment rules are also very similar, the simplified guidelines given in the earlier British codes may be applied for distribution of reinforcement in the present case also. And there is one statement here, even it is given in the manual, instructive manual, the reinforcement calculated from the bending moments obtained from section this should be provided for the full width in both directions. So you calculate the reinforcement and provide for the entire width of the slab, you had to provide that same reinforcement. This is slightly different from the practice adopted in the earlier British codes, where they divided the slab into edge strips and middle strips and provided the reinforcement, calculated reinforcement only in the middle strip. But on the edge strips, they said there isn't much bending, so minimum reinforcement is enough. Again, Mosley and Bungie and Halsey, they have suggested that that approach can be used. But these are not given in EC2. Okay, these are different ideas given by these different people trying to interpret. Here I have just given some examples of the distributions given by Mosley, etc. These are some guidelines given by the earlier British standard. Again, same things. I think some of you are already familiar with that. I think I will need a little bit more time to discuss the next few sections. I will, discuss only this slide and then I will stop here. But I have another session coming in another 10 or 12 days' time. At that time, I will take the last few slides from this presentation also, because that time I think I will not be hard pressed for time. It is about foundations, not very much. So, two-way slabs. There is this requirement. At the corner of a two-way slab, if the edges are free, not continuous, if you just load a rectangular slab like that, there is a tendency for the slab to lift up at the corner. Okay, you can imagine that, right? If you have a rectangular cardboard and supported on 4 columns at the, or even supported on all 4 sides, if you apply a load in the middle, the corners are going to lift up. But we had to prevent that in our normal slab design. We prevent that. When you prevent that, a concentrated downward tensile force will be acting at the corners. Now, that is in addition to all the bending moments and shear forces that develop. So these corner concentrated forces will cause some additional stresses to develop in the corner. They are basically resulting from a torsion that will be developing as a result of this corner concentrated force. Now, you have to take that into account and you have to provide reinforcement given in this. Provide top and bottom reinforcement. Okay, at the corner, you have to have 2 layers, top reinforcement and bottom reinforcement. In each layer, provide bars parallel to the slab edges. So in each layer, you have to have bars going in the 2 directions. In each of the 4 layers. Now, what they mean by 4 layers is, at the top, there are 2 layers now going in one direction and going in the other direction. At the bottom, there is 2 layers going in the X direction and going in the Y direction. So those are the 4 layers that they are talking about. In each of the 4 layers, the area of reinforcement per unit width, unit length, should be equal to 75% of the reinforcement required for the maximum moment in the span per unit length. So you have already found that. So 75% of that should be provided in each layer at the corner. And these are the distances over which this additional reinforcement should be provided. It is 0.2 times Lx, 0.2 times Lx in both directions. Okay. So those are the additional reinforcement required to take into account the corner concentrated forces. The area of reinforcement in 3, that is here, can be halved if one edge of the slab in the corner is continuous. Now here we have 2 discontinuous edges. This one is simply supported, discontinuous. This one is simply supported, discontinuous. But if this is continuous, if there's slab continuing over this, then this can be, the reinforcement provided there can be halved. That is from I-Struct manual. These provisions are given in other codes also. Okay, so I will take the remaining part the next time I meet you, and I will stop here. There are some chat here. Does the code give any special guidance regarding water retaining slabs? For example, swimming pool base slab against long time failure. In session number 7 or session number 8, I think Professor Anura Nanayakara is going to talk about this particular aspect, how to design for water retaining structures. So this will be handled at that time. Okay, all right. So I will stop here at slide number 78 from our set of slides. And if you have any questions, please send the questions to the Society of Structural Engineers general email address, SSE general, I think, at gmail.com. That is where you get your emails from. You send any questions you have to them, and if you mention that you want this to be addressed to the name of a resource person, that will be better, and then they will forward all such questions to us, the resource person. So we will try our best to respond either in the sessions or individually by email. So please feel free to send any questions you have to the Society of Structural Engineers general email address. All right, so thank you very much. And once again, I apologize for forgetting to give a second break. We will stop here.